In 1981, astronomers spotted something they couldn't explain. While mapping the universe, they stumbled upon a massive patch of almost nothing. No bright galaxies, no star-filled clusters, just darkness. They had discovered the Boots Void, an unimaginably vast region nearly 300 million light-years wide, and yet almost completely empty. Ever since, it's been one of the strangest mysteries in the cosmos. What could create such a gaping hole in the universe, and what does it mean for everything we think we know about space? Before we start today's journey, let us know where in the world you're watching from, and what time it is for you right now. Post it in the comments below and settle in for a cosmic ride to discover the biggest void in the universe. When most people think of the universe, they tend to picture something dazzling and crowded with stars, an enormous glowing sky filled with swirling galaxies, shining suns, and bright clouds of colourful gas and dust. Our own galaxy, the Milky Way, seems full of life and light, bursting with stars and planets. And beyond it, we imagine countless other galaxies, some spinning like giant pinwheels, others soft and oval-shaped, all lighting up the darkness with the energy of their billions of stars. When we look at the night sky on a clear evening, we see just a small glimpse of this breathtaking view, a sky dotted with tiny specks of light. These stars hint at something vast, rich, and full of wonder. From the fiery birthplaces of stars to dramatic galaxy crashes that set off bursts of light, space seems to be alive with activity. And it truly is. The universe holds an unimaginable number of stars and galaxies, far more than we can count. But this picture, as beautiful as it is, only shows part of the story. There's something just as important, yet far less talked about. Most of the universe is almost completely empty. While we often imagine space packed with shining objects, the truth is that those bright galaxies and glowing stars are scattered through an immense ocean of emptiness. For every glowing cluster, there are unimaginably vast stretches of darkness. These are the quietest regions of space, where even the fastest beams of light take millions or even billions of years to cross the distances. The amount of matter in these regions is so low, it's as if you took all the sand from every beach on Earth and spread it through a space larger than the entire solar system, and still found it mostly empty. And these quiet spaces aren't small gaps here and there. They are enormous. They're known as cosmic voids, massive bubbles in the universe where galaxies are scarce, sometimes completely absent. In these places, the bright chatter of stars and galaxies fades into a deep silence. A silence not just of sound, since sound can't travel in space anyway, but of light, heat, and gravity. To really understand these voids, we have to change the way we picture the universe. Instead of seeing it as a star-filled sky, imagine something more like a sponge. The galaxies and clusters are the dense knots and threads of the sponge, where most of the matter gathers, but the rest, the hollow parts, are the voids, and they make up a huge portion of space. These aren't just empty like the space between planets in our solar system, which still contains dust, solar wind, and light. These voids are empty on a scale that's hard to imagine. If you place the entire Milky Way inside one, it would be like dropping a single grain of sand into a massive stadium. It would be barely noticeable. Its closest neighbour might be billions of light years away. Even these empty regions are not totally devoid of matter. There are still a few lone atoms, maybe a hydrogen particle drifting here or there, and the faint glow of the cosmic microwave background, a leftover whisper from the Big Bang that happened almost 14 billion years ago. But compared to the rest of the universe, these areas are incredibly barren. A man-made vacuum chamber on Earth, designed to be as empty as possible, would be considered crowded compared to the space inside a cosmic void. In the parts of space where galaxies gather, there may be hundreds or even thousands of them, packed relatively close together. These are the galaxy clusters, connected by thin filaments where galaxies stretch like beads on a string. But inside the deepest parts of the voids, you may find only a handful of galaxies, or none at all. The rare galaxies that exist there are faint, isolated wanderers drifting alone through a black sea. Light in these places is scarce. It is like trying to light up an entire city using a single candle. But the presence of these huge empty spaces is not a mistake. They are not flaws in the universe. They are part of its design. When the universe began, it wasn't perfectly smooth. There were tiny differences in the way matter and energy were spread out. Some spots were slightly denser, others slightly emptier. Over billions of years, gravity, the invisible force that pulls everything together, started working on these small differences. In places where there was a little more matter, gravity pulled in even more. These became the stars, the galaxies, the clusters we see today. In places where there was a little less matter, there was less for gravity to pull in. So those areas didn't grow. They got stretched out and emptied as matter moved toward the denser regions. The universe itself was expanding, pulling everything apart even more, and making the voids larger and emptier. This slow, powerful process, gravity pulling in, space expanding out, sculpted the universe into the sponge-like shape we see today, a network of bright, busy clusters surrounded by vast, quiet voids. So, while the stars and galaxies get most of the attention, it's the emptiness between them that shapes the universe. The silent voids may not sparkle or shine, but they are just as important in the grand design of everything we see. The next time you look up at the night sky and marvel at the stars, remember? Behind that twinkling curtain is a vast and quiet darkness, stretching farther than the mind can grasp, the true hidden architecture of the cosmos. The mystery of these vast, silent regions goes far beyond their lack of stars or galaxies. What truly fascinates scientists is what this emptiness tells us about the invisible forces shaping the universe. Why isn't the cosmos evenly filled with galaxies like a smooth soup? Why do we find giant clusters of matter in some places, while other areas are nearly deserted? The answer lies in the invisible hands of gravity, dark matter, and dark energy. Three powerful forces that guide how matter moves and clumps together across billions of light years. In these quiet voids, there's a true physical silence. There are no newborn stars bursting to life, no galaxies whirling in dramatic dances, no powerful black holes blazing with energy at the centers of galaxies. Most of the galaxies that do exist in these regions are far apart and lonely. They don't get pulled or jostled by nearby neighbors, which means they live quieter, slower lives. Without the push and pull of frequent collisions or interactions, these galaxies might evolve differently, perhaps holding onto their gas longer or forming fewer stars over time. The idea of a completely empty space, a vacuum, has fascinated people for centuries. But cosmic voids stretch this idea to an extreme. They're not just places with a little less matter. They are enormous natural gaps in the cosmic fabric, many hundreds of millions of light-years wide. They're among the most empty places in existence, and they force us to rethink what nothingness really means. They challenge our instincts about how matter should be spread out in the universe. If you were somehow transported to the heart of one of these giant voids, far from any bright galaxy or strong gravity, the view would be eerie and unforgettable. The sky would not be full of stars or streaked with the glow of the Milky Way. Instead, it might look nearly pitch black, with only a faint star here or a dim smudge of a faraway galaxy there, barely visible even through powerful telescopes. The closest bright object could be so far away that its light has travelled for hundreds of millions of years just to reach your eyes. You wouldn't be seeing a lively, glowing present. You'd be peeking into a ghostly cosmic past. That chilling visual emptiness contributes to what scientists call the cosmic silence. A quiet so complete, so absolute, it feels like it has its own presence. But this silence is not only about what you see, or don't see, it's also about gravity. Gravity does reach across all of space, but it weakens with distance. And in these voids, the nearest massive objects are so far away that their pull is barely felt. The matter that does exist in these voids is left mostly undisturbed, floating freely as the universe expands. In fact, because of the strange push of dark energy, these already empty regions are expanding even faster than the rest of space. The temperature in these cosmic cavities is just a few degrees above absolute zero. That's minus 459 degrees Fahrenheit. There are no stars nearby to warm things up, no clouds of gas to compress and heat. Only the faint glow left over from the Big Bang, the cosmic microwave background, adds a whisper of warmth. It's a place of extreme cold, darkness, and stillness, where the silence is almost frozen into space itself. Yet, despite how empty they seem, these cosmic voids are treasure troves for scientists. Because they contain so little ordinary matter, they allow researchers to study dark energy more clearly. In crowded areas of space, gravity from stars and galaxies can interfere with how dark energy acts. But in these wide, quiet voids, there is almost nothing to block or confuse the effects of dark energy. This makes them perfect places to study how this strange force might be pushing the universe apart. By examining the size, shape, and growth of voids over time, scientists hope to uncover new clues about one of the biggest mysteries in all of physics. So, even though they look like nothing, these voids are far from meaningless. Their vast stillness actually points us toward the deepest truths about the universe, how it formed, how it evolves, and what invisible forces are guiding it. These cosmic gaps are not just holes in space, they are windows into the universe's hidden design, full of silent stories and subtle clues. For thousands of years, people looked up at the night sky and saw only what their eyes could take in, tiny pinpricks of light scattered across the darkness. Our early understanding of the universe was limited to what we could see without tools, just stars shining above us. But everything began to change when the first telescopes were built. Suddenly, new worlds and fainter stars appeared. Over time, we discovered that our home, the Milky Way galaxy, was just one of many. The universe, once thought to be small and simple, kept growing larger in our minds. By the middle of the 20th century, astronomers had begun to understand just how massive the universe truly is. They believed it was filled with galaxies more or less evenly spread throughout space, like dots sprinkled across a huge sheet. It was a neat and elegant picture, one that made sense at the time. But then, something unexpected happened. A discovery came along that completely changed that picture. It showed that the universe wasn't evenly filled with galaxies after all. In fact, it revealed that there were enormous patches of space, giant holes, where galaxies were almost completely missing. This discovery opened a whole new chapter in our understanding of how the universe is built. And at the heart of that revelation was the identification of a cosmic giant, the Bootes void. This remarkable discovery was made in the early years of the 1980s by a group of astronomers led by Robert Kirshner. His team included August Umler Jr., Paul Schechter, and Stephen Schechtman. Together, they were working on a large project to study how galaxies are spread out across space. But this wasn't a matter of just looking through a telescope and counting stars. To truly map the universe, they needed to figure out not only where galaxies appeared in the sky, but also how far away they were from Earth. This extra dimension, distance, would help them create a kind of three-dimensional map, showing how galaxies cluster, stretch into long filaments, and leave behind vast empty areas. To do this, they used a powerful tool called Redshift. Redshift works a bit like how sound changes when a police siren moves away from you. The sound gets lower because the waves are stretched out. With light, something similar happens. When a galaxy moves away from us, the light it gives off is stretched out, shifting toward the red part of the spectrum. The more stretched it is, the faster the galaxy is moving away, and the farther away it must be. This idea goes back to the early 20th century, when the astronomer Edwin Hubble discovered that nearly every galaxy is moving away from us. He also found that galaxies farther away move faster. This connection between speed and distance, now known as Hubble's law, allowed scientists to calculate how far off a galaxy is just by measuring its redshift. So, using Redshift, Kirshner and his team observed thousands of galaxies. They pointed their telescopes at a particular area of the sky and gathered the faint light coming from very distant galaxies. Then, they broke this light into a rainbow of colours, called a spectrum, to look for specific patterns. These patterns, like a fingerprint, told them what elements were in each galaxy, and more importantly, how much the light had been stretched. With this information, they calculated how far each galaxy was. As they collected more and more data, they gradually built up a detailed three-dimensional picture of galaxy locations in that region of the universe. But as they kept mapping the galaxies, they noticed something strange. In one part of the sky, specifically in the direction of the constellation Bootes, there were almost no galaxies at all. This wasn't because their instruments failed or because the region was hidden by dust. Their telescopes were working fine, and they were still seeing galaxies nearby and far beyond that area. But right in the middle, there was a giant stretch of space that was shockingly empty. It looked like a huge bubble in the cosmos, a spherical zone hundreds of millions of light-years across with barely anything inside. By the year 1987, after years of hard work and careful study, they formally announced their findings in a major scientific paper. They named this huge empty space the Bootes Void, after the constellation in whose direction it lies. The Bootes Void turned out to be one of the largest cosmic structures ever found. Early estimates showed that it was about 250 million light-years in diameter. To grasp just how large that is, consider this. Our entire Milky Way galaxy is only about 100,000 light-years across. That means you could fit thousands of Milky Way-sized galaxies inside the Bootes Void, and yet, this entire region holds only a handful of them. The discovery was a turning point. It showed that the universe is not just filled with stars and galaxies scattered like sugar in tea. Instead, the universe is full of structure, dense clusters and long filaments of galaxies that surround vast, empty regions like the Bootes Void. This led scientists to think about the universe in a new way. Rather than being uniform, the cosmos appears to be shaped like a gigantic web. Galaxies are strung along threads, and these threads twist and wind through enormous bubbles of nothingness. This is what scientists now call the cosmic web. The Bootes Void, one of its most striking features, helped reveal this hidden architecture of the universe. It showed that even in the vastness of space there are patterns, beautiful, strange, and sometimes haunting, in the way matter is spread. The scientific world responded with a mix of amazement and excitement when the Bootes Void was discovered. It wasn't just the size of the void that stunned researchers, it was what it meant for our understanding of the universe. Before this, many of the simpler models of the cosmos had assumed that matter was spread out more or less evenly, like butter on a slice of bread. But this discovery changed everything. Here was a gigantic region of space, stretching hundreds of millions of light-years across, that was almost completely empty. That kind of emptiness didn't fit the neat, balanced picture many scientists had in mind. This unexpected finding sparked a wave of new research. Scientists began to take a closer look at the earliest moments of the universe, trying to figure out how such an enormous empty region could have formed. Questions about the roles of dark matter and dark energy, those invisible forces that shape the structure and fate of the universe, became even more urgent. Researchers wanted to know if these mysterious components could help explain why some parts of the universe are filled with clusters of galaxies, while others, like the Bootes Void, are eerily silent. The discovery also showed how powerful and important large-scale redshift surveys could be. Before this, most astronomers had focused their attention on individual galaxies or small groups of them. But the Bootes Void made it clear that to truly grasp the universe's structure, scientists needed to map far larger stretches of space. It was a shift in thinking. The universe wasn't just a scattered collection of stars and galaxies. It was a vast, interconnected system, full of patterns, areas of great density and areas of near-total emptiness. In the years following the discovery, astronomers continued to scan the skies with better tools and more advanced redshift surveys. These later observations confirmed that the Bootes Void was very real. They also revealed other similar voids, some smaller, but still significant in size. Surprisingly, scientists even spotted a few lonely galaxies inside the Bootes Void. These rare galaxies were not completely surrounded by nothingness, but floated like tiny islands in a cosmic sea. Their isolation makes them incredibly valuable to scientists, because they offer a rare chance to study how galaxies evolve on their own, far away from the usual gravitational tug-of-war found in crowded regions of space. The techniques and tools developed during the study of the Bootes Void have since become essential in the effort to map the universe. Thanks to this breakthrough, scientists have discovered countless other structures, some densely packed with galaxies, others almost completely empty. The Bootes Void became more than just a strange dark patch in the sky. It became a symbol of scientific progress, a reminder of how much we still have to learn, and how much the universe can surprise us when we dare to look deeper. Its discovery in the early years of the 1980s did not just reveal a hole in space. It revealed a hidden part of the universe's design, something far more complex and mysterious than anyone had guessed. It showed us that the cosmos is not evenly filled, but shaped by both brilliant bursts of matter and enormous whispering voids. The Bootes Void reminds us that sometimes It's in the quietest, emptiest places that the universe speaks the loudest truths. The universe is unimaginably vast, a realm so immense that the usual ways we measure distance, like kilometers or miles, quickly become useless. In our everyday lives, we think in terms of distances we can walk, drive, or fly. But in the grand theatre of the cosmos, such units are far too small to make sense. When scientists talk about galaxies, or even more gigantic structures made of many galaxies, they need something far bigger. That's where the light year comes in. A light year is the distance that light, which moves faster than anything else we know, can travel in the span of one Earth year. Light moves at a breathtaking speed of about 300,000 kilometers every second. Over the course of a year, that adds up to about 9,460,000,000,000 kilometers. Just imagine that. A single light year equals nearly 10 trillion kilometers. We need this enormous unit because the universe is so huge that even something as fast as light takes a long time to get from one place to another. But even with light years, the numbers involved in describing the cosmos quickly grow so large they seem almost impossible to picture. Our brains are wired to understand a trip across town, a road across a country, or maybe even a flight across the globe. But how do we grasp a journey that would take light millions of years? This brings us to one of the most mind-blowing features ever discovered in the universe, the Butter's void. This isn't just a large gap in space, it's a colossal hole in the structure of the universe, a place so empty and so vast that it stretches the limits of human imagination. When astronomers first mapped it out, they estimated it to be about 250 million light-years wide. Pause and let that number settle in. 250 million years is how long it would take light to cross from one side of the void to the other. To give some context, Earth itself is only about 4,500,000,000 years old. That means light has to travel for more than 5% of Earth's entire lifetime just to get across the Butter's void. That alone gives you an idea of how enormous this space is, not just large, but truly gargantuan, even by cosmic standards. And keep in mind, this isn't just a flat gap like a hole in a sheet of paper. It's a three-dimensional sphere, an almost perfectly round bubble of nothingness inside the universe. To understand just how immense this void is, let's compare it to something we know a little better, our home galaxy, the Milky Way. The Milky Way is a stunning spiral galaxy filled with between 100 billion and 400 billion stars, not to mention vast clouds of gas and dust, and a supermassive black hole sitting quietly at its centre. From one end to the other, the Milky Way stretches about 100,000 light-years. Now, if the Butter's void is 250 million light-years wide, and the Milky Way is 100,000 light-years across, then it would take 2,500 Milky Ways lined up end to end just to span the diameter of the Butter's void. Picture that, 2,500 galaxies, each filled with billions of stars all arranged in a line just to bridge this one massive emptiness. That image makes the sheer emptiness of the Butter's void even more astonishing. If you place the entire Milky Way galaxy right in the centre of it, our whole cosmic neighbourhood would be nothing more than a tiny speck, swallowed by a sea of darkness. From the edge of such a lonely Milky Way in the middle of the void, if you looked out into space, the night sky would look heartbreakingly empty. You wouldn't see the familiar arch of stars that make up our galaxy. You might not even see any nearby galaxies at all. The closest galaxy could be hundreds of millions of light-years away, so far that it might appear as just the faintest ghostly blur, if it were visible at all, even through the most powerful telescope. In such a place, the sense of cosmic isolation would be overwhelming. There would be no nearby galactic neighbours, no gravitational dances between galaxies, no explosions of supernovae from nearby stars lighting up the skies. Just cold, silent darkness. The Butter's void would live up to its name perfectly. It would truly be a void, a vast and nearly perfect example of cosmic loneliness. The gaps between galaxies in this region are not just a little larger than usual. They are so wide that the normal idea of galactic neighbourhoods simply doesn't apply anymore. This isn't a slightly empty region. It's a place that has been drained of galaxies over billions of years. Let's step back even further and consider a larger view of our cosmic surroundings. The Milky Way isn't alone. It belongs to a family of galaxies called the Local Group. This small cluster includes our Milky Way, the Andromeda Galaxy, the Triangulum Galaxy, and about 50 dwarf galaxies, all tied together by gravity. From one side to the other, the local group spans about 10 million light-years. That sounds like a lot, but again, it's tiny compared to the Bootes void. If you tried to stretch local groups across the width of the Bootes void, you could fit about 25 of them in a row. This tells us that the Bootes void is not just empty when compared to a single galaxy. It's empty even when compared to clusters of galaxies. In the local group, galaxies interact with each other, tugging and twisting through gravity, forming stars and triggering bursts of activity. But inside the Bootes void, such interactions are almost non-existent simply because there are so few galaxies around. This is the true scale of cosmic emptiness. It's not just that there's less stuff in the Bootes void, it's that the entire architecture of galaxies and clusters that make up the universe seems to have skipped over this region. Whatever processes shaped the large-scale structure of the cosmos left this particular area astonishingly blank. The Bootes void stands as a monument to the enormous, mysterious, and sometimes lonely nature of the universe, a vast invisible chasm hidden behind the glittering veil of stars that we see when we look up at the night sky. To truly understand just how gigantic the Bootes void is, we can compare it to other colossal structures in the universe, structures made up of galaxies bundled together, like galaxy clusters and even bigger ones called superclusters. A galaxy cluster is like a cosmic city, packed with hundreds or even thousands of galaxies. All of these galaxies are held together by gravity, forming a dense and massive structure. These clusters can stretch across distances from around 3 million to 30 million light-years. One well-known example is the Virgo cluster, which lies relatively close to us in cosmic terms. The Virgo cluster spans about 10 million light-years across, and our own local group of galaxies is slowly drifting in its direction. Now, here's the incredible part. Even a galaxy cluster as large as the Virgo cluster would look tiny when placed inside the Bootes void. You could line up 10, 50, or even 100 of these giant clusters side by side and still not completely fill the width of the Bootes void. It's like putting a row of skyscrapers across the Grand Canyon. No matter how tall they are, the canyon swallows them in scale. The difference in density is striking. A galaxy cluster is like a busy, crowded metropolis, while the Bootes void is like an endless desert with almost nothing in sight. But the universe doesn't stop at galaxy clusters. It builds even larger formations called superclusters. A supercluster is an enormous web of galaxy clusters and smaller galaxy groups all loosely connected by gravity. These are the largest known structures in the universe, forming vast filaments and cosmic highways of galaxies that can stretch for hundreds of millions of light-years. One such structure is the Laniakea supercluster, which includes our own Milky Way galaxy. Laniakea spans about 500 million light-years, an unimaginably vast distance. Now, the Bootes void has a diameter of about 250 million light-years, which is about half the size of Laniakea, but still bigger than many other famous superclusters. This means that the Bootes void isn't just bigger than single galaxies or small galaxy groups, it is bigger than some of the grandest galactic structures in the entire universe. This fact alone makes the Bootes void stand out as something truly extraordinary. It's not just an empty gap between galaxies, it's a vast, cosmic absence that matches the scale of the universe's largest and most complex structures. The universe is not evenly filled with galaxies like raisins in a cake. Instead, it is more like a sponge, with thick galaxy-rich areas separated by enormous empty bubbles. The Bootes void is one of the most massive of those bubbles, and here's where things get even more mind-blowing. The Bootes void isn't just wide, it's a three-dimensional sphere, like a bubble floating in space. That means it has volume, not just area. To understand how empty this bubble truly is, let's think in terms of volume. The volume of a sphere depends on the cube of its radius. The Bootes void has a radius of about 125 million light-years. If we compare that to our Milky Way galaxy, which has a rough radius of about 50,000 light-years and is shaped more like a flat disk, the difference becomes staggering. Even if we imagine the Milky Way as a perfect sphere just to make the math easier, the Bootes void would still be billions of times larger in volume. For every Milky Way-sized sphere, the Bootes void could hold billions of them. It's like comparing a single grain of sand to an entire mountain range. And remember, this enormous space isn't packed with billions of galaxies. It's nearly empty. That's what makes a void different from just a gap between galaxies. It's an enormous space where galaxies are missing from an entire volume, not just from a patch of sky. Now imagine trying to travel across this enormous emptiness. Even if we had a spaceship that could fly at 1/10 the speed of light, which is far beyond our current technology, it would still take more than 2.5 billion years to travel from one side of the Bootes void to the other. For comparison, life on Earth has existed for about 3.5 billion years, so this journey would take almost as long as the entire history of life on our planet. But in reality, our fastest spacecraft, like the Voyager probes, travel at speeds of only tens of kilometers per second. At that speed, crossing the Bootes void would take far, far longer than the entire current age of the universe, which is around 13.8 billion years. The idea of travelling such a distance is beyond what we can even grasp. Even communication would be incredibly difficult. Light, which is the fastest thing in the universe, would take hundreds of millions of years to travel across the void. If someone were inside the Bootes void trying to send a signal to another galaxy, it would take longer than human civilization has existed for that signal to arrive. Anyone living inside the Bootes void, if such a place could support life, would be completely alone. The nearest galaxies would be tens of millions of light years away, and the only thing visible in the sky might be faint, ancient starlight from galaxies so far away that their light took hundreds of millions of years to arrive. The loneliness would be unimaginable. But when scientists call the Bootes void a void or an empty space, they don't mean it's completely empty like a vacuum. In the cosmic sense, empty just means that there is a lot less stuff there than in other parts of the universe. Even in the deepest parts of the Bootes void, there are still some hydrogen atoms drifting around, the occasional photon of light from the cosmic microwave background, and of course, dark matter, which we cannot see but know is there. Still, compared to the average density of matter in the universe, usually a few atoms per cubic meter, the Bootes void might have less than 1 atom per cubic meter, maybe much less. That makes it one of the most underdense regions ever discovered. And yet, even in this emptiness, astronomers have found a few lonely galaxies, maybe around 60 of them, floating inside the Bootes void. These galaxies are incredibly isolated, separated from each other by tens of millions of light years. In any other part of the universe, that would be a huge distance, but in the Bootes void, it's the norm. This incredible emptiness is not just an odd curiosity. It tells us something profound about the way the universe is structured. It is not evenly filled with galaxies. It is not smooth. It is clumpy, uneven, and full of surprises, filled with bright, rich regions of light, but also with vast, silent stretches of darkness. The Bootes void is one of those silent stretches, and by studying it, we are forced to change how we think about the universe. We see that the cosmos is not only a place of shining stars and swirling galaxies, but also of deep silence and magnificent emptiness. To understand where the Bootes void is located in the vastness of the universe, we need to think about something called cosmic geography, the way the universe is arranged on a grand scale. Just like Earth has its own structure with continents, oceans, mountains and valleys, the universe also has a kind of architecture, only on an unimaginably larger scale. The stars and galaxies are not just scattered randomly in all directions. Instead, they form an enormous interconnected pattern often called the cosmic web. This cosmic web is made up of huge, delicate strands, which scientists call filaments. These filaments are packed with galaxies, like beads on a thread, stretching for hundreds of millions of light years. Where many filaments come together, they form massive intersections or nodes where galaxies crowd together in dense clumps. But between these threads and intersections lie vast, dark and empty regions. These enormous spaces are called cosmic voids, and they are like the valleys of the universe, huge areas where there are very few galaxies, stars or even much matter at all. One of the biggest and most famous of these empty regions is the Bootes void. It is a massive, nearly empty bubble in the cosmic web, and understanding where it is means first understanding where we are. Let's begin our cosmic journey right here, on Earth. Earth is one of 8 planets that orbit around the Sun, which is a middle-aged star. But our Sun is not alone. It is just one of hundreds of billions of stars that make up our Milky Way galaxy. The Milky Way is a beautiful spiral-shaped collection of stars, dust and gas that stretches about 100,000 light-years from one end to the other. Our Sun is located about 27,000 light-years from the centre of this spiral, tucked into one of its spiral arms. But the Milky Way itself is not alone either. It is part of a small group of galaxies called the Local Group. This group includes the Milky Way, our closest large neighbour the Andromeda Galaxy, and about 50 smaller dwarf galaxies. The Local Group spans a region about 10 million light-years across. Now, the Local Group is being slowly pulled toward a much bigger gathering of galaxies called the Virgo Cluster, which is about 55 million light-years away from us. And both the Local Group and the Virgo Cluster belong to a much grander region of space called the Laniakea Supercluster. This supercluster is a huge gravitationally connected region of the universe that spans roughly 500 million light-years. It's like our cosmic continent, a vast area filled with galaxies, clusters and filaments, all held together by gravity. So, our full cosmic address would be Earth, Solar System, Milky Way, Local Group, Virgo Cluster, Laniakea Supercluster. Once we understand where we are in the universe, we can then look out into the distance to find the Bootes Void. From our point of view on Earth, it appears in the direction of a constellation called Bootes, also known as the Herdsman. Now, constellations are just patterns of stars that look like they are grouped together in the night sky, but in reality these stars can be very far apart in three-dimensional space. So when we say that the Bootes Void is in the direction of Bootes, we mean that if you aim a telescope toward that area of the sky, and then measure how far away the galaxies are, you'll come across a huge and astonishing emptiness. A gigantic three-dimensional spherical region where almost nothing exists. It's not just a dark patch of sky, but a massive bubble-like hole in the fabric of the universe. The centre of the Bootes Void is estimated to be about 700 million light-years away from Earth. That means the light coming from its centre began travelling toward us 700 million years ago, a time when life on Earth was still mostly in the ocean, and complex creatures were just starting to appear. So when we look at the Bootes Void, we're not only looking far away in space, but also far back in time. This giant, silent region stands as one of the most mysterious and fascinating features in the grand design of the universe. The Bootes Void is not something we can find just beyond the edges of our galaxy. In fact, it lies unimaginably far away, far beyond our local galactic neighbourhood, even beyond the boundaries of our massive home supercluster, known as Laniakea. To reach even the closest edge of the Bootes Void, one would have to travel several 100 million light-years through space. That makes it an incredibly distant feature in the vast landscape of the cosmos. If we could lay out a gigantic map of the universe with Earth roughly at the centre, the Bootes Void would appear as a huge, dark, empty bubble, located far away from us, far beyond not just the Milky Way galaxy, but even beyond the entire supercluster we belong to. It is a structure of the far universe, not something nearby or local. The Bootes Void is a perfect example of what scientists call a cosmic void. These voids are enormous, empty regions that help shape the large-scale structure of the universe. To picture this structure, imagine a giant sponge or a web of soap bubbles. The parts of the universe that glow with stars and galaxies, the galaxy clusters and superclusters, gather along the outer layers of these bubbles. These glowing threads and walls are called filaments, and they're where matter has clumped together over billions of years, pulled in by gravity. But the spaces in between, the hollow parts of the sponge, are the voids. These are vast stretches of space where very few galaxies exist. The Bootes Void is one of the biggest and clearest of these empty spaces. Imagine, for a moment, a vast highway system in space. The filaments are like busy cosmic highways, packed with the hustle and bustle of galaxies racing along them. Now imagine a massive, abandoned roundabout or empty plaza in the middle of these roads. That's the Bootes Void. It's like a forgotten district in the heart of the universe, a place where very little happens, but which still plays a vital role in the overall structure. The Bootes Void shows us that matter in the universe is not spread out evenly, but instead arranged into an elaborate foamy design. All around the Bootes Void, astronomers have spotted some of the universe's largest structures. While the void itself is eerily empty, it is encircled by denser regions of the cosmic web, like a hollow in a sponge surrounded by thick walls. For instance, Parts of the Hercules supercluster and the Corona Borealis supercluster are located nearby, though still hundreds of millions of light-years away. These mighty collections of galaxies act like the rocky shores that define the edges of a cosmic ocean. And that's exactly what the Bootes Void is, a gigantic ocean of emptiness, separating the continent-sized superclusters of galaxies. Over billions of years, the gravity from these surrounding structures has slowly pulled matter toward them, draining the Bootes Void and making it even emptier. As the universe expands, this process continues, stretching the void even larger. So, the Bootes Void is not just an empty place. It's a major part of how the universe is organized, marking the vast open areas between the bright, crowded regions of galaxies. To better understand this, let's compare it to something more familiar, a map of Earth. On such a map, continents represent places where land, like galaxies and stars, is found in abundance. The oceans, wide and mostly empty of land, represent the cosmic voids. The Bootes Void is like one of the largest oceans on this cosmic Earth, an enormous basin of emptiness, sitting between the land masses of galaxy-filled regions. Just as a ship travelling through the middle of the Pacific Ocean is unlikely to spot any land, a galaxy wandering through the heart of the Bootes Void would find itself alone in a vast sea of darkness. This comparison helps us see the Bootes Void not as a random patch of nothing, but as an important part of the universe's grand design. Though many other cosmic voids have been discovered, ranging in size from around 10 million to several hundred million light-years across, the Bootes Void remains one of the most famous. It was among the first truly massive voids ever found, and when astronomers first detected it, its sheer size was shocking. This helped make it a standard example, a kind of model void used to help understand others like it. It may not be the only one of its kind, but it stands out because of its clarity and how dramatically it revealed just how empty some parts of the universe can be. Its place in the cosmic web is typical for large voids, surrounded by bright filaments of galaxies and glowing clusters that form the scaffolding of the universe. By studying how the Bootes Void fits into this grand pattern, astronomers can test their ideas about how the universe has evolved. For example, by looking at how galaxies are arranged along the void's edges and how the void itself has grown over time, scientists can learn more about the mysterious force called dark energy. This invisible energy is believed to be stretching space itself, helping to enlarge these empty regions. So, the Bootes Void is more than just an empty patch. It is a key feature of the cosmic landscape. Its location, its shape, and its relationship to the surrounding galaxy-filled filaments give astronomers valuable clues about the invisible forces shaping our universe. It stands as a quiet but powerful witness to the dynamic processes that have carved the universe into a web of light and shadow, of matter and emptiness, over billions upon billions of years. Gravity is often called the weakest of the four fundamental forces in nature. That may sound surprising, especially when we think about how it seems to control everything from falling apples to the movements of planets. But despite being weak compared to other forces like electromagnetism or the strong nuclear force, gravity has quietly shaped the largest and most magnificent structures in the entire universe. Over the course of billions of years, gravity has been at work, pulling things together slowly, patiently, and relentlessly. It has taken clouds of the loose gas and turned them into glowing stars. It has pulled those stars into swirling galaxies. It has then gathered those galaxies into even bigger structures, clusters, superclusters, and long, thread-like filaments that form the grand structure of the cosmos. This intricate pattern, which astronomers call the cosmic web, stretches across the universe like a vast, invisible spiderweb. But gravity doesn't just build up things, it also tears things apart, or rather clears them out. Strangely enough, gravity is also responsible for creating enormous empty regions of space, known as cosmic voids. These are vast, dark areas where very few galaxies exist. A famous example is the Bootes Void, a cosmic desert that is so huge and so empty, it's hard to believe such a place exists. So, gravity is not only the force that gathers matter into dense cosmic cities, but it's also the one that clears out the enormous wildernesses between them. In this way, gravity acts as a cosmic sculptor, shaping the universe by both pulling matter together and creating vast emptiness between those gatherings. At its most basic level, gravity is just a pull between two things that have mass or energy. The more massive something is, the stronger its pull, and the closer two objects are, the stronger the gravitational force between them. This rule was first discovered by Isaac Newton in the late 17th century, and later improved upon by Albert Einstein in the early 20th century through his theory of general relativity. This simple but powerful force is what causes an apple to fall to the ground. But it's also what makes galaxies spin and drift apart over billions of light years. After the Big Bang, about 13.8 billion years ago, the universe was extremely hot, incredibly dense, and almost perfectly smooth. But almost is the key word. There were tiny bumps, very slight differences in density, like gentle ripples in a calm sea. Imagine this early universe as a smooth ocean, with very tiny rises and dips. In the areas where there was just a little more matter, gravity was a little bit stronger. That stronger pull slowly began to gather more matter toward those areas, and as more matter collected, gravity grew stronger, attracting even more matter. This snowball effect, where tiny lumps grow larger and larger, is called gravitational instability. These slightly denser spots eventually grew into the first building blocks of structure in the universe. Over millions and then billions of years, they became galaxies, clusters, and the long filaments of the cosmic web. But what about the places that started off with less matter? There, gravity was weaker. As the denser areas began pulling in more material, they essentially stole matter from their emptier neighbours. The low-density regions couldn't hold on to their sparse material, and it slowly flowed away. These regions became emptier and emptier over time. Gravity, in trying to gather things together in some places, was also draining matter from others. That's how the great cosmic voids formed, like the Bootes void, an enormous empty area that was left behind as matter was pulled away by its denser surroundings. Now, to truly understand how all of this happened, we need to talk about something mysterious: dark matter. Dark matter is a type of matter that doesn't give off light, doesn't reflect it, and doesn't absorb it. In fact, it doesn't interact with light at all, which is why we can't see it directly. But we know it's there because of how it affects the things we can see. Dark matter makes up about 85% of all matter in the universe. That means the stars, planets, gas, dust, everything we see makes up less than 15%. The rest is invisible, but its gravity is very real. When the universe was still young, those tiny density ripples were mainly ripples in dark matter. These little clumps of invisible matter became deep gravitational wells that pulled in both dark matter and regular matter. Ordinary gas and dust fell into these invisible pits, cooled down, and eventually formed stars and galaxies. Without these dark matter clumps, regular matter wouldn't have been able to gather fast enough to form anything meaningful. The universe would have remained mostly smooth, with no galaxies, no stars, and likely no life. So, the cosmic web, this giant lacy pattern of filaments, clusters, and empty regions, is really a dark matter structure. The long filaments are dark matter highways, drawing galaxies along their length. The clusters are giant, heavy knots of dark matter that act like galactic hubs. And the voids, like boots, are places where even the dark matter is sparse. The galaxies we can see, those glowing dots in telescope images, are just tiny lights sitting on top of a much bigger invisible structure made of dark matter. The reason the Bootes void is so empty is likely because it started out with very little dark matter, and since it didn't have enough gravity to attract and hold on to matter, it gradually lost even more material to nearby, denser regions. Over billions of years, it became a vast and lonely part of the cosmos. If we zoom into smaller scales, we see that the same rules of gravity apply. Inside giant clouds of gas, gravity pulls atoms together, forming stars. Those stars pull on each other, creating star clusters. On a larger scale, billions of stars and clouds of gas and dust are pulled together into galaxies, like our own Milky Way. Even the graceful spiral shape of our galaxy is shaped by gravity, all of it held together by a surrounding halo of dark matter. As we look at even bigger parts of the universe, gravity keeps on doing its quiet but powerful work. It's not just stars and planets that are pulled together. Entire galaxies, like our Milky Way and its neighbour Andromeda, also feel each other's pull. Over time, these galaxies are drawn toward one another and come together to form small groups, such as the one we live in, called the local group, But it doesn't stop there. These galaxy groups are themselves pulled toward even larger clumps of matter. Many of them come together to form galaxy clusters, huge gatherings that can hold hundreds or even thousands of galaxies. The gravity in these clusters is so strong that it tugs on galaxies nearby, pulling them inward toward the crowded center. Even more fascinating, these massive clusters are often joined by long, thin threads made up of galaxies. These threads are called filaments, and they stretch across space like the strands of a cosmic spiderweb. Galaxies move along these filaments, following the invisible paths carved out by gravity, flowing toward the biggest and heaviest clusters. Altogether, this enormous network of clusters and filaments forms what scientists call the cosmic web, a vast web-like structure stretching across the universe. This is where gravity has been especially successful, gathering matter into dense connected shapes and slowing down the natural expansion of space in these areas. But not all of space is filled with galaxies and clusters. There are also the voids, giant, dark and nearly empty parts of the universe. These are the opposite of the filaments. As gravity pulls matter into the cosmic web, it leaves behind huge stretches of nothingness. One of the most famous of these empty regions is the Bootes void. The Bootes void is unbelievably large and incredibly empty. It was born as a slightly less dense region in the early universe, a place with less dark matter than surrounding areas. Over the course of billions of years, gravity acted like a cosmic vacuum. The stronger gravity from the surrounding filaments and clusters slowly pulled matter away from this underdense region, making the Bootes void even emptier. It's as if space itself was drained, leaving behind a hollow shell. Inside this immense emptiness, only a few galaxies remain. These are often called lonely galaxies. They either formed from the small patches of leftover matter within the void, or they were simply too isolated and too tiny to be pulled out by the gravitational tug of nearby structures. Their lonely existence is living proof of just how powerful gravity can be. It literally cleared out everything around them and left them stranded in the dark. Now, one of the most important things to understand about gravity is that it works very slowly. Its effect is not immediate. It takes a very, very long time to shape the universe. In fact, the universe itself has been evolving for about 13.8 billion years since the moment of the Big Bang. In the beginning, the universe wasn't perfectly smooth. Some areas had just a little more matter than others. These tiny differences in density, barely noticeable at first, were enough for gravity to get to work. Over billions of years, gravity pulled on the slightly denser areas, causing them to grow. Slowly but surely, these regions became galaxies, clusters, and filaments. At the same time, the less dense regions, the voids, were emptied out even more. Gravity may be the weakest of the four fundamental forces in nature, but its slow, steady, and patient pull has completely reshaped the cosmos. It turned tiny wrinkles in the early universe into enormous structures that can hold themselves together, even as space itself continues to expand. And in doing so, gravity not only built the bright and shining parts of the universe, but also carved out the vast and silent darkness between them. The universe often brings to mind a breathtaking picture, one filled with shining stars scattered across a velvet black sky, countless galaxies spinning like glowing whirlpools, and majestic clouds of gas called nebulae lit up by the birth of newborn stars. We picture a cosmos that is alive and full of motion, bursting with colour, energy, and activity in every direction. In this picture, grand spiral galaxies like our own Milky Way hold hundreds of billions of stars, many of them surrounded by planets, moons, and possibly even life. This beautiful, energetic vision is certainly real, but it only tells one side of the cosmic story. There is another side, one that is quiet, cold, and profoundly empty. For every bright cluster of stars or galaxies, there are enormous regions of space where there is almost nothing, places where the fabric of the universe itself seems stretched thin. These are the vast, dark deserts of the cosmos, and one of the most mysterious and extreme of them is known as the Bootes void. The Bootes void is not just a space that is less full, it is staggeringly empty by cosmic standards. Scientists use the word sparse to describe it, but in truth, that word barely captures how empty it really is. Even the best vacuum chambers created on Earth, which are considered extremely empty, still contain millions of atoms in every cubic meter. In comparison, the average density of the entire universe is already extremely low, only about 1 hydrogen atom per cubic meter when you spread all the matter and energy evenly across space. That's a level of emptiness hard to imagine. The air you're breathing right now contains trillions upon trillions of atoms in each cubic centimeter. And remember, a cubic meter holds 1,000,000 cubic centimeters. Now, imagine a region of space that is even emptier than that tiny average. This is exactly what scientists found in the Boots void. In the heart of this vast dark area, the amount of ordinary matter, like atoms, stars and galaxies, can be 10 times lower than the already thin cosmic average. In other words, there may be far less than 1 atom per cubic meter, perhaps just a few lonely atoms floating in a space as large as a building, or even as big as an entire city block. This is not just empty, it is emptier than anything we can create or easily comprehend. What truly stands out about this sparseness is not just the lack of atoms, but the near total absence of luminous matter, the kind that shines and gives off light. Galaxies, stars, glowing gas clouds, all the things we usually associate with the universe are incredibly rare in the Boots void. In a region of space that might normally hold hundreds or even thousands of galaxies, the Boots void might contain only a handful. These are not just galaxies that are farther apart. They are galaxies that exist in near isolation, like islands in a vast, dark sea. If you could somehow find yourself inside the Booties void and look up at the sky, the scene would be eerily dark. Instead of a glittering sky filled with starlight, you might see only a few faint smudges of light. Distant galaxies so far away that they would appear as dim, lonely specks, separated by hundreds of millions of light years. There would be no glowing nebulae, no fiery stellar nurseries, and no brilliant galactic collisions lighting up the darkness. The silence would not just be one of sound, it would be a silence of light. This deep emptiness is not a random accident. It is the result of how matter was arranged in the very earliest moments of the universe's history. Over 13 billion years ago, when the universe was still young, it was not perfectly smooth. There were tiny differences in the density of matter. Some areas were just slightly thicker than others. The denser spots pulled in more material through the force of gravity, growing into the long filaments and huge galaxy clusters we see today. But the less dense regions had the opposite fate. As the universe continued to expand, these slightly underfilled areas were stretched further and further, causing even more matter to drift away toward denser regions. Over billions of years, this process carved out the great voids, giant cosmic hollows like the Booties void. Even though these places seem utterly empty, they are not completely without matter. One of the most important and mysterious forms of matter in the universe, dark matter, is still present inside these voids, although it too is more thinly spread than in other regions. Dark matter doesn't shine or reflect light, and we can't see it directly. But we know it's there because of its gravitational pull. It helps shape the overall structure of the universe, even in these nearly empty places. Its behaviour is also affected by those early tiny differences in density, so even voids like Booties carry the imprint of the universe's earliest moments. More mysterious still is something called dark energy. Unlike dark matter, which pulls things together, dark energy pushes space itself apart. It is believed to be responsible for the fact that the expansion of the universe is speeding up. Scientists think that dark energy is evenly spread throughout all of space, filling galaxies, clusters, and yes, even the voids. In fact, voids like the Boots void may be the best places to study dark energy, because there is so little matter to interfere with its effects. In these silent, vast regions, the influence of dark energy can become more visible, more noticeable, and more measurable. So when scientists call a place in the universe sparse, they mean something far beyond what we normally think of as empty. They are describing regions where the ingredients of everything, stars, planets, atoms, light, are so rare and scattered that even calling them places seems strange. These voids are reminders that the universe, though filled with brilliance and wonder, is also shaped by silence and darkness. They are the deep shadows behind the glowing lights, the vast hollows that give the cosmic web its structure. And the Booties void, one of the largest and most haunting of them all, stands as a quiet monument to the powerful forces that shaped everything we see. inside a vast and nearly empty region of space like the boot is void, the gravitational environment is completely different from what we see in crowded areas like galaxy clusters. In a galaxy cluster, there are hundreds or even thousands of galaxies packed closely together. These galaxies are always pulling on each other with their gravity. Sometimes they swing past one another, sometimes they tug and twist each other into new shapes, and occasionally they even crash into one another and merge. These powerful gravitational interactions help shape how galaxies grow and change. They affect the birth of new stars, the shape of the galaxies, and how gas is spread out inside them. But inside the Booty's void, things are much quieter and lonelier. Only a few galaxies exist in this enormous stretch of space, and they're so far apart that their gravity barely reaches each other. The nearest big groups of galaxies are located hundreds of millions of light years away. That's an unimaginable distance. So far that their gravitational pull on the galaxies inside the void is extremely weak, almost like a whisper in the dark. This means that the galaxies and matter floating inside the void mostly feel a gentle tug from the faint dark matter scattered through the void, and a tiny pull from the very distant galaxy filaments on the outer edges. Because of this deep isolation, the galaxies within the Booty's void are not disturbed by outside forces. They are free to drift with the universe's overall expansion, spreading out even more slowly and peacefully than their counterparts in crowded areas. They evolve in a calmer, quieter way, untouched by the chaos and violence of galactic collisions or nearby gravitational chaos. It's a place of stillness in a universe that is often wild and loud with activity. But it's important to understand that cosmic voids like the Boot's void are not just the usual empty spaces we find between galaxies. Even in a galaxy cluster or a galaxy filament, the space between galaxies is mostly empty, but not entirely. Those intergalactic regions, even though thin and vast, are still relatively close to dense parts of the universe, and they often contain a very faint fog of gas known as the intergalactic medium. This gas can even be heated by nearby galaxies that are actively forming stars or by powerful black holes at their centers. Cosmic voids are something else entirely. They represent emptiness on a much greater level. They are not just empty spaces between a few galaxies. They are enormous zones that stretch between entire superclusters of galaxies. In these voids, there are fewer galaxies, fewer stars, fewer black holes, and almost no powerful sources of energy. The intergalactic medium here is even thinner and colder than in other places because there's barely anything to heat it up. The lack of gravity, matter, and energy sources defines these regions and sets them apart from the rest of the universe. Voids are like vast deserts in the cosmic landscape, not just quiet, but almost completely abandoned by the usual building blocks of galaxies. The extreme emptiness of the Booty's void, and of other similar voids, makes them incredibly difficult to study. Because there are so few stars and galaxies inside them, very little light comes from these areas. Astronomers have to use some of the most powerful telescopes in the world, and they must observe these regions for many hours or even days to collect the tiny amounts of light that do exist. The galaxies inside the voids are so rare and so faint that studying them takes extraordinary effort and patience. Yet this very emptiness is what makes the Booty's void so scientifically valuable. In places where there is almost no ordinary matter, we can better understand the influence of something else: dark energy. Dark energy is a mysterious force that scientists believe fills all of space and is pushing the universe to expand faster and faster. In crowded parts of the universe, it is difficult to separate the effects of gravity from the effects of dark energy. But in the peaceful, low-gravity environments of voids, dark energy can be studied more clearly. By looking at how quickly voids like the Booty's void are expanding and how matter is spread out inside them, scientists can collect important clues about how the universe is growing and changing over time. They can test different theories about what dark energy is, how it works, and why the expansion of the universe is speeding up. In the middle of one of the most empty and silent places in the universe, the Booty's void, something surprisingly beautiful and strange exists: a small group of lonely galaxies. Even though this region is known for its deep darkness and lack of stars and glowing matter, it is not completely empty. Hidden inside this enormous cosmic desert are a few galaxies scattered across its vastness. Astronomers call them void galaxies, or lonely galaxies, because they live in almost total isolation, far away from the crowded places where most other galaxies can be found. These galaxies are like tiny boats drifting in an endless dark ocean, so far from any neighbours that they seem to float alone in space. In most parts of the universe, galaxies live in busy environments. They pull on each other with gravity, sometimes crashing together or merging to form new shapes. But inside the Bootes void, these lonely galaxies have no such interactions. They exist in peace, undisturbed by the usual cosmic drama. This gives scientists a rare and special opportunity. They can study how galaxies grow and change when they are left entirely on their own, without the push and pull of nearby galactic neighbours. When astronomers first discovered the Bootes void in the year 1981, they believed it was almost completely empty. Early surveys showed little more than a dark stretch of sky. But over time, as technology improved and telescopes became more powerful, researchers began to notice faint traces of light, signals from a few distant galaxies hiding in the darkness. Today, scientists estimate that about 60 galaxies have been identified within the Bootes void. Considering how massive this area is, that number is shockingly small. To understand just how empty the Bootes void is, let us make a comparison. If galaxies were spread out evenly across the universe, then a region the size of the Bootes void should contain thousands, or even tens of thousands of galaxies, especially ones the size of our Milky Way. Instead, there are only about 60. These few galaxies are not clustered together. Instead, they are spread far apart, often separated by 10 million or even 20 million light-years from one another. Imagine standing on a planet in one of these galaxies and looking up at the night sky. You would see almost nothing, just a few faint patches of distant light, like whispers in the dark. The glowing threads of the cosmic web, the large-scale structure of the universe, would be almost invisible, tiny pinpricks of light scattered across a nearly black sky. Because these galaxies live in such a quiet and empty place, they are quite different from those in busy galactic neighbourhoods. One of the most noticeable differences is in their shapes. In crowded galaxy clusters, galaxies often bump into each other, or pass close enough to feel strong gravitational forces. These encounters can rip away gas, squash or stretch a galaxy's shape, or even cause sudden explosions of starbirth. But in the Bootes void, these lonely galaxies are rarely disturbed. They don't get pulled or pushed around, and they almost never crash into anything. Because of this, many of them still have their original shapes. Most are faint spirals or irregular galaxies that look more untouched, like relics from an earlier time in the universe. Their structure is mostly controlled by what happens inside them, rather than by outside forces. Another important difference is how they form stars. To make new stars, a galaxy needs large supplies of cold gas and dust. In crowded places, this gas can be stripped away by hot intergalactic material or stolen during galactic collisions. When that happens, the galaxy can no longer make new stars and begins to age. These galaxies are often called red and dead because they stop shining with the blue light of young stars and instead glow dimly with older, redder stars. But the lonely galaxies of the Bootes void do not face this problem. Since there are no nearby galaxies and no dense gas clouds to strip away their material, they can keep their star-making fuel for a very long time. As a result, these void galaxies tend to have slower, steadier star formation. They are like quiet workshops, slowly crafting new stars without interruption. Many appear bluer than galaxies and clusters, showing that they still have young stars being born. This calm, ongoing star formation gives scientists a window into what galaxies might look like if they were left to evolve naturally over billions of years, without the chaos of galactic collisions or tidal forces. However, studying these lonely galaxies is not easy. First, they are incredibly far away from Earth, and because they are not forming huge numbers of bright new stars, they appear very dim. The light they send out takes hundreds of millions of years to reach us, and by the time it gets here, it is faint and hard to detect. To study them properly, astronomers need to use some of the world's most powerful telescopes, both on Earth and in space, and keep the cameras pointed at one spot for many hours, sometimes even days. Getting time on these telescopes is very competitive, so each chance to observe one of these galaxies is precious. Second, their isolation makes them harder to study in other ways. In normal galaxies that live in clusters, or along the filaments of the cosmic web, astronomers can use nearby bright galaxies to help with measurements or to observe things like gravitational lensing. But in the Bootes void, there are no helpful neighbours. Each lonely galaxy must be studied on its own, using only the faint light it produces. There's also a problem with how few of these galaxies we have actually found. With only about 60 known galaxies in the Bootes void, it's hard to know if they represent all types of void galaxies, or just the ones we're able to see with our current instruments. It's very possible that there are many more faint small galaxies hiding in the darkness that we simply haven't found yet. This means that our current list might be biased toward the larger and brighter ones, leaving out an entire population of smaller or more mysterious void dwellers. Still, scientists continue to carefully collect data. They study the redshifts of these galaxies to figure out how far away they are and exactly where they sit inside the Bootes void. They examine their light using spectrographs to learn about what they're made of, how fast stars are forming inside them, and how their material moves. Every observation adds a little more to our understanding. Even though it can be difficult to study them, galaxies that live alone, far from the crowded neighbourhoods of the universe, hold incredible value for science. These solitary galaxies, often drifting in enormous cosmic voids, offer rare clues that help astronomers answer some of the biggest questions about how galaxies are born, grow, and change over time. Think of these lonely galaxies as the universe's version of a control group in an experiment. Most galaxies are packed close together in busy areas like clusters or along cosmic filaments, where they constantly interact with each other, pushing, pulling, colliding, and even merging. But lonely galaxies, isolated in vast, quiet regions of space, live without much outside interference. By comparing what happens inside these isolated galaxies to those in crowded areas, scientists can start to figure out which changes come from a galaxy's own inner workings and which are caused by its surroundings. For example, suppose there's a galaxy in a dense cluster that has stopped making new stars because it has lost all its gas. Then imagine another galaxy, about the same size and age, sitting quietly inside a cosmic void. If that lonely galaxy still has its gas and is still forming stars, the difference suggests that something in the crowded cluster, like a force called Ram pressure stripping, which blows gas out of galaxies, may be responsible. In this way, astronomers can better understand the different paths galaxies take, depending on where they live. Over billions of years, these environmental effects can shape a galaxy's future in dramatic ways. But that's not all. Because lonely galaxies have spent most of their lives in peace, without bumping into their neighbours or merging with them, they may have kept more of the original features they had when they first formed. This makes them like ancient time capsules, preserving clues from the very beginning of the universe. By studying them, scientists may learn what galaxies were like in the earliest times, especially in areas where matter was sparse. Looking ahead, the future of studying these cosmic recluses is incredibly exciting. New generations of telescopes, both in space and on the ground, are opening up the universe in ways we could only dream of before. One of the most powerful of these is the James Webb Space Telescope. This telescope, which looks at the universe in infrared light, is so sensitive that it can spot very faint and very distant galaxies that older telescopes simply couldn't see. It was launched in the year 2021 and has already begun transforming our view of the cosmos. Meanwhile, enormous new ground-based telescopes, fitted with cutting-edge technologies like adaptive optics and extremely sensitive detectors, are also on the way. These observatories will help astronomers discover many more lonely galaxies, even the smaller and dimmer ones that are now hidden from our view. With larger samples to study, scientists will be able to look more closely at how these galaxies store gas, how they form stars, and what their inner structures look like. Altogether, this will help paint a clearer, fuller picture of how galaxies grow and survive when they're truly on their own. Perhaps most fascinating of all is imagining what the universe might look like from inside one of these lonely galaxies. Imagine a distant planet, orbiting a star in such a quiet corner of the cosmos. If intelligent life were to develop there, their night sky would be completely different from ours. On Earth, we look up and see a sky filled with stars, planets, and the glowing band of the Milky Way stretching across the heavens. But for beings in a lonely galaxy, maybe one floating inside the vast emptiness of the Bootes void, the view would be far more empty. The Milky Way would be so distant that it wouldn't be visible at all. Their night sky would be mostly black, with only a few stars from their own galaxy scattered across it. With powerful telescopes, they might spot the faintest twinkles from other isolated galaxies, hundreds of millions of light-years away, but these would be tiny, barely visible points of light. For such beings, the universe might feel like a lonely, desolate place. They might believe that their galaxy was the only one in existence, never knowing about the vast web of billions of galaxies stretching far beyond their reach. Their understanding of the cosmos would be shaped entirely by the quiet, empty world they saw around them. For much of human history, our understanding of the universe was quite limited. In the beginning, we could only see individual stars twinkling in the night sky. Later on, we discovered that those stars were not just scattered randomly, but were part of much larger systems called galaxies. For a time, even galaxies themselves were thought to be floating aimlessly through the vast emptiness of space, like tiny specks of dust drifting through a dark, silent room. But as time went on, our telescopes became more advanced and powerful. Scientists also developed better tools to measure distances across the universe with incredible precision, and what they uncovered completely changed the way we look at the cosmos. Instead of finding a random jumble of galaxies, they revealed something truly breathtaking, an enormous, organized, and interconnected structure stretching across the entire universe. This incredible arrangement, made of galaxies, invisible dark matter and mysterious forces, is called the cosmic web. To picture it, imagine a gigantic spider web, not flat but three-dimensional, spanning distances so vast that our minds can barely grasp them. The galaxies are not sprinkled evenly throughout space like sugar in a bowl. Instead, they gather along long, thin threads of this web, lighting up the cosmic structure like tiny lanterns. Where the threads cross and knot together, galaxies clump in large groups, forming what could be described as enormous cities of stars. And in between these glowing strands are the dark, empty spaces, the great cosmic voids, like the holes in a sponge or the spaces between tree branches in a forest at night. Now, this grand web cannot be captured in a single photograph. It's too big and too complex. Instead, scientists have had to piece it together slowly by mapping the locations of millions upon millions of galaxies one at a time. Every galaxy becomes a tiny dot on an immense cosmic chart. When enough dots are connected in 3 dimensions, a pattern emerges, a web-like structure that shows how galaxies are distributed across the universe. This map is one of the most beautiful and profound discoveries in the history of astronomy. The cosmic web is made up of 3 main parts, each with its own special role in shaping the universe. The first and most visible parts of the cosmic web are the filaments. These are long, thread-like structures that stretch across the universe like the arms of a great galactic octopus. Each filament can extend for hundreds of millions of light-years, so long that even light, travelling at over 299,000 kilometers per second, would take hundreds of millions of years to cross from one end to the other. Galaxies are not randomly placed within these filaments. They are strung along them like glowing beads on a necklace. Our own home, the Milky Way galaxy, is nestled inside one of these filaments, located in a relatively quiet part of the cosmic web. These filaments serve as the highways of the universe, channels through which galaxies and matter flow toward denser regions. But these highways aren't straight or smooth. They twist, bend, and branch, shaped by the invisible pull of gravity over billions of years. Along their lengths, galaxies gather into smaller clusters and groups, constantly in motion, tug toward the larger structures nearby. These filaments form the skeleton of the universe, the hidden framework upon which galaxies are built, shaped, and moved. The discovery of these vast, glowing threads helped astronomers understand that the universe is not chaotic, but carefully structured. Seeing how these filaments stretch across space gave us new insight into how galaxies came to be where they are. The next major part of the cosmic web are the clusters, also called nodes. These are the places where several filaments come together, like the intersections of highways or the knots in a spider web. And just like a busy city where roads meet, galaxy clusters are full of activity. Galaxy clusters are the heaviest and most crowded places in the universe. They can contain hundreds, sometimes thousands of galaxies, along with huge clouds of hot gas that shine brightly in X-rays, and enormous amounts of invisible dark matter. These clusters are held together by their own powerful gravity, forming the largest known structures that are bound by gravity. One famous example is our own local group, which includes the Milky Way. This small group of galaxies is part of a much larger structure called the Laniakea Supercluster, a vast region full of galaxy clusters like shining jewels in the sky. Inside these clusters, galaxies are close enough to constantly interact. Sometimes they crash into one another, sometimes they pull gas from their neighbours, or even merge entirely. These interactions cause galaxies to grow, change shape, and evolve quickly. The gravitational pull of a galaxy cluster is so strong that it draws in other galaxies from the filaments around it, like a city drawing people in from the countryside. These clusters are the most crowded and lively parts of the cosmic web, and their existence balances perfectly with the quiet emptiness of the voids. And now, we come to the most mysterious and haunting parts of the cosmic web, the voids. These are the enormous, nearly empty spaces that lie between the filaments and clusters. They are the silent oceans of the universe, where galaxies are few and far between. One of the most famous examples is the Bootes void, a colossal bubble of near nothingness. It is so large that light would take hundreds of millions of years to cross from one side to the other. In these regions, there are hardly any galaxies at all, sometimes fewer than 1/10 the number found in average parts of the universe. They are not completely empty. There may still be stray atoms or the occasional lonely galaxy drifting through, but compared to the bustling filaments and clusters, these voids are deserts of space. What's even more fascinating is that these voids are growing larger over time. As the universe expands and gravity pulls matter toward the denser parts of the web, the voids stretch and become emptier. The galaxies that once might have existed inside them have been drawn away, leaving behind vast cosmic silence. Inside a void, a single galaxy might exist in total isolation. No neighbours, no nearby clusters, no bright companions. These lonely places help scientists understand just how unevenly matter is spread across the universe, and why some galaxies are shaped by interaction, while others live undisturbed lives for billions of years. Together, the filaments, clusters, and voids form the grand structure of everything we know, the cosmic web. It is a universe-sized network that has taken billions of years to grow into its current form. Galaxies are not scattered like confetti in a storm. They are carefully woven into a cosmic tapestry, shaped by gravity, dark matter, and time. The mystery of how gigantic empty regions, like the Bootes void, fit into the grand structure of the universe is not just a side question. It is at the very heart of how the universe is built. These voids are not random patches of nothingness scattered around by chance. Instead, they are essential parts of a much larger, carefully woven pattern called the cosmic web. To picture this better, imagine stretching a large piece of rubber fabric. As you pull on one part of it, the area you're stretching becomes denser, while other parts become thinner and emptier. Something very similar happened in the early universe. As gravity began pulling matter together into long, thread-like structures called filaments, and into dense collections called galaxy clusters, other regions were left behind, emptier, thinner, and more spacious. These leftover regions are the voids. The Bootes void is one of the most stunning examples of this process. It is an enormous region in space where very little matter gathered, due to the specific starting conditions of the universe, combined with the powerful effects of gravity and the never-ending expansion of space. You can think of it like a giant bubble in a foamy sponge. This bubble is surrounded by walls, not solid, visible barriers, but rather zones where galaxies have clumped together in greater numbers. These walls mark the edges of the void and are made of the very filaments that form the skeleton of the cosmic web. So, the Bootes void is not floating outside the universe's structure, it is part of it. In fact, it plays a crucial role in showing us how matter is spread out unevenly on the largest scales imaginable. It is a massive hole in the sponge-like layout of the cosmos. The filaments and clusters are the dense, spongy parts, while the voids are the empty pockets. This strange but beautiful cosmic foam is how the universe organizes itself. To understand where the Bootes void fits in, it helps to know where we are. Our home galaxy, the Milky Way, belongs to a small collection of galaxies called the local group. This group, in turn, is part of an even larger structure known as the Laniakea supercluster, which stretches across a huge region of space like a vast continent of galaxies. We do not live in a void. Our galaxy is tucked inside a fairly crowded part of the cosmic web, a filament that is slowly being pulled toward a denser, more massive region near the centre of the Laniakea supercluster. The Bootes void lies far beyond this neighbourhood. It is located hundreds of millions of light-years away, more than 300 million light-years in fact. It sits in a very different part of the cosmic map. Compared to the busy cities of galaxies we live in, the Bootes void is more like a lonely desert, a reminder of just how varied and enormous the universe really is. From bustling galactic highways to silent cosmic wastelands, the universe holds every kind of environment imaginable. By knowing where we are, we get a clearer view of just how vast and diverse the cosmic landscape truly is, and how important these voids are in the big picture. Now, this grand cosmic web is not just an idea dreamed up by scientists. It has been observed and confirmed using some of the most advanced tools in astronomy. Thanks to powerful telescopes and huge surveys that measure something called Redshift, astronomers have been able to carefully map the three-dimensional locations of millions of galaxies. Redshift helps them figure out how far away each galaxy is, based on how its light stretches as it travels through the expanding universe. By combining all of these distance measurements, scientists have built detailed three-dimensional maps of the universe. And when these maps are put together, something incredible appears. The cosmic web comes into view as clear as a picture. Filaments show up as long chains of galaxies linking together like cosmic bridges. Clusters shine brightly where those chains intersect, and in between, huge dark spaces appear where galaxies are almost entirely missing. These are the voids. The Bootes void was one of the very first and most striking examples ever found. Its sheer size and emptiness helped prove that the universe is not evenly filled with matter, but instead arranged in a complex web-like pattern. It was a major piece of evidence that showed scientists that voids, filaments, and clusters all fit together to create a vast cosmic design. Today, with even better telescopes and more advanced surveys, these maps are becoming sharper and deeper, revealing the cosmic web in more detail than ever before. They continue to confirm what scientists predicted, that voids are not accidental gaps. They are vital parts of how the universe is built. The universe we see today is filled with an astonishing variety of structures. From the tiniest building blocks of matter, atoms, to massive galaxy clusters stretching across millions of light years, everything is arranged in patterns that are both beautiful and complex. But the universe didn't always look this way. If we travel back in time to the very beginning, right after the Big Bang, over 13 billion years ago, we find a universe that was shockingly different. It was unimaginably hot, extremely dense, and, most importantly, almost perfectly smooth. Picture an enormous pot of perfectly blended cosmic soup, with matter and energy mixed together so evenly that no part stood out. There were no stars, no galaxies, no clusters, no empty gaps, just a glowing fog of particles and light, all spread out in nearly the same way everywhere. Yet today, when we gaze into space, we see a universe filled with shining galaxies gathered into long, twisting filaments, while between them lie vast, dark voids, immense empty regions like the famous Bootes void, which spans hundreds of millions of light-years. How did we get from that smooth, hot soup to the rich, lumpy, web-like structure we see today? This question lies at the heart of modern cosmology. The answer, as incredible as it may seem, begins with unimaginably tiny differences that existed right from the start. Differences so small they were almost invisible, but they were enough. Over billions of years, with the help of gravity and the continuous stretching of space, these tiny variations grew into the mighty cosmic structures of today. The great empty voids, including the Bootes void, are not just random gaps. They are natural consequences of this long cosmic journey. Let's begin this story at the very earliest moments, when the universe was still younger than a fraction of a second. Although the early universe was almost completely smooth, it wasn't perfectly so. Thanks to quantum mechanics, the science that describes the strange behavior of things at the tiniest scales, we know that there must have been tiny bumps and dips in the distribution of matter and energy, even in this smooth soup. These slight fluctuations in density and temperature, far too small to notice with the naked eye, were like gentle ripples on an otherwise still pond. These ripples weren't created by accident. Scientists believe they came from quantum events that took place when the universe was smaller than a single atom. Then came an event known as cosmic inflation, a sudden, dramatic expansion that took place in less than a trillionth of a second. This expansion stretched those microscopic ripples across the universe, turning them into the seeds from which everything else would grow. In some places, there was just a tiny bit more matter than average. In others, there was a tiny bit less. And from these almost invisible differences, the structure of the entire cosmos began to take shape. The force that began shaping the universe using those tiny differences was gravity, the invisible pull that draws things with mass together. Even though the density differences were incredibly small, gravity started working on them right away. In areas with slightly more matter, gravity's pull was a little stronger, and it began pulling in even more matter from nearby regions. These slightly denser spots grew heavier and more crowded over time. Meanwhile, areas with a little less matter experienced weaker gravity. As nearby matter was pulled away toward denser regions, the less dense spots became even emptier. It's a bit like a snowball effect, but with matter being unevenly gathered. The rich, in terms of matter, got richer, while the poor got poorer. Gravity acted like a cosmic vacuum cleaner, sucking material away from the underfilled areas and piling it up in the regions that already had more. Slowly, over billions of years, this process made the dense regions denser and the empty ones emptier, forming clusters of galaxies on one hand and vast empty voids on the other. This process has a name: gravitational instability. It's a key idea in understanding how the universe's structures grow. You can think of it like a delicate house of cards. A small shake, a little tremor, is all it takes to set off a collapse. In the case of the cosmos, those small tremors were the early fluctuations in density. Over time, gravity magnified them. Regions with more matter began to collapse inward, drawing in gas and the mysterious substance known as dark matter. These became the glowing threads and knots of the cosmic web, the filaments of galaxies and giant clusters we see scattered throughout the universe today. At the same time, the less dense areas began to expand faster than the rest of the universe. As gravity pulled material away from them toward the growing dense regions, they lost more and more of their contents. These regions, emptied out by the gravitational hunger of their neighbours, became the cosmic voids. They are not just leftover spaces, they are vital parts of how the universe organised itself. The entire structure of the universe emerged from this simple but powerful process of gravity sorting matter into crowded and empty zones. But there's another major character in this grand story, one we cannot see directly. It's called dark matter. Unlike ordinary matter, dark matter doesn't shine, reflect, or block light. It doesn't interact with electromagnetic forces, which means telescopes can't detect it the way they do stars or gas clouds. But we know dark matter is there because of the way its gravity shapes the motion of galaxies and the structure of space itself. Scientists estimate that dark matter makes up about 85% of all the matter in the universe. That means for every bit of regular matter, like the stuff that forms you, the Earth, the stars, and everything we can see, there's more than 5 times as much dark matter. In the early universe, it was these slightly denser patches of dark matter that first began to clump together. Their gravity pulled in even more dark matter and then drew in ordinary matter as well. These early clumps acted like invisible scaffolding, frameworks on which galaxies and clusters could form and grow. And just as dark matter helped build the dense parts of the universe, it also shaped the empty ones. Areas with less dark matter ended up becoming the voids. Although these voids still contain some dark matter, they have much less of it than the denser filaments and clusters. The presence, or absence, of dark matter played a central role in deciding where galaxies would form and where empty spaces would be left behind. In this way, dark matter quietly set the stage for the grand cosmic drama, directing where light would shine and where darkness would remain. So, the vast emptiness of the Bootes void, and others like it, is not a cosmic accident. It is the natural result of billions of years of subtle differences growing under the influence of gravity, guided by the invisible hand of dark matter and shaped by the expansion of space itself. From the tiniest ripples in a sea of fire, the universe built everything: bright galaxies, majestic clusters, and the dark, silent spaces in between. Besides the pull of gravity, there is another powerful force that plays a major role in shaping the empty spaces of the universe. This force is the ongoing expansion of the cosmos itself. The universe is not still or frozen in place. Ever since the Big Bang, which happened more than 13 billion years ago, space has been stretching outward in all directions. This means that the distance between galaxies is steadily increasing, and the universe keeps getting bigger with time. This cosmic expansion plays two different roles depending on the scale you're looking at. On smaller scales, like inside galaxies or within galaxy clusters, gravity is strong enough to hold things together. Even as space stretches, gravity keeps stars, gas, and dark matter clumped into these dense regions. But on much larger scales, such as the vast reaches between galaxy clusters, the expansion of space becomes the stronger force. And here's where the story of the great voids truly begins. In the earliest days of the universe, some regions had just a little bit less matter than others. These slightly emptier areas are what would one day become cosmic voids. As space expanded, these underdense regions stretched faster than the denser ones. The small amount of matter inside them was pulled farther and farther apart, making them even more empty over time. This thinning out of matter due to the universe's expansion is called cosmic dilution. You can picture it like inflating a balloon with tiny dots drawn on it. As the balloon grows, the dots move farther from one another. The dots that started far apart end up even more distant as the balloon continues to inflate. This is exactly what happens inside voids. The stretching of space keeps pushing the few particles inside them away from each other, making the voids grow larger and emptier as time goes on. These voids are not just curious blank spots. They are a natural result of how space itself behaves. The formation of these enormous empty regions, along with the filaments and clusters of galaxies that surround them, is part of a grand cosmic design called the cosmic web. But this vast and beautiful structure didn't form overnight. It took billions upon billions of years. To figure out how it all came together, scientists use incredibly advanced computer simulations. These simulations act like miniature digital versions of the universe. They begin with the conditions believed to exist shortly after the Big Bang: tiny ripples in the density of matter, the mix of ordinary matter and invisible dark matter, and the ever-expanding space. Then, by letting the simulation evolve over billions of years, scientists watch as gravity and expansion interact with these ingredients. Slowly but surely, they see something amazing emerge: long strands of matter called filaments, crowded regions full of galaxies called clusters, and vast open areas almost completely empty, the voids. What's remarkable is that the structures these simulations produce look strikingly similar to what astronomers see when they look into the real night sky. A particularly striking example is the Bootes void. This gigantic and lonely region is one of the emptiest known parts of the universe. Its sheer size and deep emptiness make it stand out, but it's not an accident or a mystery. Simulations show that such voids naturally form when the universe evolves under the laws of physics we already understand, especially when we include the effects of dark matter and dark energy, the invisible forces shaping the cosmos. These simulations are more than just cool visual tools. They let scientists test their ideas. For example, they can change the amount of dark matter or the strength of dark energy in their models to see how the structure of the universe would look different. This helps researchers understand not just what the universe looks like today, but why it looks that way, and what rules were in play from the very beginning. But computer models alone are not enough. Observations of real cosmic voids like the Bootes void are just as important. Astronomers carefully measure the positions of galaxies, figure out how far away they are, and study the rare galaxies that live inside these quiet regions. This data allows scientists to test whether their simulations are accurate. When they see that real voids behave just like the ones in their models, it gives them strong confidence that their understanding of cosmic structure is on the right track. The Bootes void, in particular, stands as one of the most compelling pieces of evidence. Its vast emptiness and massive size are not strange or unexpected. In fact, they are exactly what we would predict if the laws of physics, such as gravity and cosmic expansion, were acting on tiny early universe ripples over billions of years. When we look up at the night sky or peer into the universe through powerful telescopes, what we see is only a tiny part of what's really out there. We see shining stars, swirling galaxies, glowing clouds of gas, and all the things made of what scientists call ordinary matter. This ordinary matter is made up of atoms, like hydrogen, helium, and heavier elements. It's the same stuff that forms planets, people, oceans, trees, and even the air we breathe. And it's the only kind of matter our telescopes can directly detect because it interacts with light. It either reflects it, absorbs it, or gives it off. But here's the astonishing truth revealed by modern cosmology, which is the science of studying the universe as a whole. All of that visible matter, the glowing stars, the galaxies, and everything we can see, is just a small slice of the universe's total matter. Most of the matter in the cosmos is something completely invisible, something mysterious, and yet incredibly powerful. It's called dark matter, and it plays a huge role in shaping the universe. Even though we can't see dark matter, we know it's there. It doesn't shine, reflect, or block light. It doesn't interact with light at all, which is why it's called dark. It's like a ghost that doesn't leave a visual trace. But we can observe its powerful pull on the things we can see. Galaxies, for instance, spin much faster than they should if they were made only of ordinary matter. This tells us that something invisible, something much heavier than all the stars and gas we can detect, is holding them together with its gravity. We also see the light from faraway galaxies bend around invisible mass, a phenomenon called gravitational lensing. This bending only makes sense if there's far more mass than we can see. And perhaps most dramatically, we see the universe forming a giant cosmic web, a huge, tangled structure of filaments, clusters, and vast empty regions called voids. None of this could have formed the way it did without dark matter. Scientists estimate that about 85% of all the matter in the universe is dark matter. That means that for every one handful of normal matter, there are about 5 or 6 handfuls of this unseen stuff. It is the main sculptor of the large-scale structure of the universe. The story of how this cosmic structure came to be began shortly after the Big Bang, which happened around 13.8 billion years ago. At that time, the universe was extremely hot, incredibly dense, and mostly smooth. But it wasn't perfectly smooth. There were tiny, barely noticeable differences in how much matter was packed into different regions. Some spots had just a little more matter, while others had slightly less. These tiny differences are believed to have come from quantum fluctuations, tiny ripples, in the universe's earliest moments. What's important is that these early ripples were present in both ordinary matter and dark matter. But because dark matter made up most of the mass, its gravity had a much stronger effect. Where there was a bit more dark matter, its gravity pulled in even more matter. Where there was less, it couldn't pull as effectively. These small differences in dark matter density were the starting points, the seeds, of everything we see today: galaxies, clusters, filaments, and even the empty spaces in between. Over billions of years, gravity began to do its quiet, persistent work. In places where there was a little more dark matter, gravity slowly pulled in more and more material from the surroundings. This process is called gravitational instability. Small clumps of dark matter grew larger and heavier as they gathered more matter around them. Eventually, these clumps formed invisible dark matter halos, like deep gravity wells or invisible mountains, where ordinary matter like gas and dust collected. As that ordinary matter gathered, it cooled down, clumped together, and formed the very first stars and galaxies. The galaxies we see today are still nestled inside those enormous dark matter halos, held there by gravity. Think of the dark matter as the hidden skeleton or scaffolding of the universe. It's what gives galaxies their structure, and what pulls them together into larger formations like galaxy clusters and long filaments that stretch across space. Without dark matter, the universe would be a very different place. The ordinary matter alone wouldn't have had enough gravity to overcome the powerful force of cosmic expansion. Instead of forming stars and galaxies, the matter might have stayed spread out, forming a thin soup of gas, with no bright galaxies or grand structures at all. But dark matter didn't just help form galaxies. It also played a crucial, though less obvious, role in creating the universe's vast empty regions, called voids, like the enormous Bootes void. Just as there were spots with slightly more dark matter, there were also regions with slightly less. These places had weaker gravity. So, as matter was being pulled into the denser areas, it was drained out of the underdense ones. Picture this like a cosmic drainage system. The regions with more dark matter acted like gravitational sinks, pulling in material from their surroundings. Meanwhile, the regions with less dark matter were gradually emptied out, as they couldn't hold on to their matter strongly enough. Over time, matter flowed away from these underdense areas and collected in the growing clusters and filaments. This flow of matter sculpted the cosmic web, carving out the vast, dark voids between the glowing galaxies. The Boots void, one of the largest known voids, is a powerful example of this. It likely began as a region with a significantly lower concentration of dark matter than average. Over billions of years, as gravity pulled matter toward the richer, denser areas, this part of the universe was left behind, almost emptied of both dark matter and ordinary matter. Today, it stretches across space as a colossal, hauntingly empty region, a silent monument to the quiet, invisible forces that shaped our cosmos. So, while we cannot see dark matter, it is absolutely essential. It is the silent architect of the universe, the hidden hand that built the galaxies, stretched the filaments, and carved out the voids. Without it, the universe we know, the beautiful, complex web of stars and galaxies, would never have come to be. Even in the deepest and loneliest parts of the universe, like the enormous Bootes void, dark matter has not completely vanished. It is still there, quietly lurking in the shadows, but in much smaller amounts than what we usually find across the universe. While the Bootes void may seem like a vast and empty space, it is not totally hollow. It is simply far more thinly spread out, especially when it comes to dark matter. In places like galaxy clusters or cosmic filaments, the long thread-like structures that connect galaxies, dark matter tends to gather and clump together more tightly. This creates strong gravitational fields that can pull in galaxies' gas and other matter. But inside a void, the dark matter is more spread out and much less dense. This means that the pull of gravity in such areas is weaker and more gentle. This has a big effect on the rare, lonely galaxies that happen to live inside the Bootes void. These galaxies are like islands floating in a quiet sea. They are not surrounded by thick clouds of dark matter like galaxies in busy clusters, nor are they tugged around by the powerful gravity of nearby cosmic structures. Instead, they evolve in peaceful isolation, far from the bustling traffic of the cosmic web. Even though they are alone, these galaxies still have their own small halos of dark matter. These halos act like invisible glue, holding their stars and gas together. Without this dark matter, the galaxies would likely fall apart. Still, the space around them remains calm, gravitationally speaking. It is as if these galaxies exist in a cosmic wilderness, where the usual noise and tugging of gravity is quieted down to a faint whisper. And yet, the presence of dark matter, even in such sparse areas, reminds us that no part of the universe is ever truly untouched by its influence. This unseen material continues to shape the cosmos, even in the most subtle and far-reaching ways. It stretches across the universe like an invisible web, connecting everything with threads of gravity. We can also see the importance of dark matter when we look at the structure of the universe on the larger scales. The cosmic web, with its bright clusters, long filaments, and vast empty voids, is not just made of visible galaxies. All of it is built upon an enormous hidden framework of dark matter. The galaxies we see with our telescopes are just the glowing tips of a much larger invisible iceberg. In contrast, the voids are like cosmic valleys, where this dark matter web is either extremely thin or almost absent. Computer models that simulate how the universe grew after the Big Bang, an event that happened over 13 billion years ago, show us something fascinating. These simulations only match what we observe in real space if we include dark matter in the calculations. When scientists try to simulate the universe using only ordinary matter, like atoms and gas, the results are too flat and uniform. The rich texture of filaments, clusters, and voids simply does not appear. This strong match between what computers predict, when dark matter is included, and what telescopes observe gives scientists some of the most powerful proof that dark matter is real. It shows that this mysterious stuff is not just a theory. It is a vital part of the universe's history and structure. Without it, the universe would not look the way it does. Even the Bootes void itself, a gigantic, almost empty bubble of space that spans hundreds of millions of light years, stands as a silent witness to the influence of dark matter. It shows that dark matter does not only gather and build things up, it also has the power to create vast hollow spaces by pulling matter away, leaving behind darkness and quiet. In this way, dark matter is like a hidden artist, painting the universe not only with bright strokes of stars and galaxies, but also with the wide, shadowy brushstrokes of emptiness. By studying these enormous cosmic voids, astronomers are able to learn more about this mysterious invisible force. Through them, we begin to understand how dark matter shaped the grand design of the universe, both the places where light gathers and the places where it fades into silence. Just as dark matter quietly shapes the structure of the universe by pulling things together with its invisible gravity, there is another mysterious force that works in the opposite direction. This strange energy is known as dark energy, and instead of pulling, it pushes, it stretches space itself. While dark matter gathers things together like a cosmic glue, dark energy acts more like a cosmic wind, blowing everything farther and farther apart. Its influence is especially noticeable in the vast empty spaces of the universe, the cosmic voids, such as the famous Bootes void. Even though we cannot see dark energy, its presence is felt across the entire universe. It fills every corner of space, even in places where there is almost no matter at all. And it plays a major role in how fast the universe is expanding. In fact, it is the main driver of that expansion. While dark matter helps form galaxies and galaxy clusters by pulling matter together with its strong gravitational grip, dark energy stretches the fabric of the universe, causing the space between galaxies, and especially the emptier regions, to grow faster and faster over time. This unexpected and mysterious force was only discovered a few decades ago, and it changed how scientists think about the universe. Before its discovery, astronomers believed that the universe's expansion, which began with the Big Bang around 13.8 billion years ago, should be slowing down because of the gravitational pull of all the matter within it, just like a ball tossed into the air eventually slows and falls back down. But then something astonishing happened in the late 1990s. Two separate teams of astronomers were studying faraway supernovae, which are powerful explosions of dying stars. These explosions serve as standard candles, objects whose brightness we already understand very well. By comparing how bright they appear from Earth, astronomers can figure out how far away they are. They also measured the redshift of the light from these supernovae, which tells us how fast the galaxies that host them are moving away from us. The scientists expected to find that the expansion of the universe was gradually slowing down, but instead they found something shocking. Those distant supernovae were dimmer than expected, which meant they were farther away than they should have been. This surprising result revealed that the expansion of the universe is not slowing down at all, it's actually speeding up. The universe was accelerating. This discovery shook the scientific world and led to a revolutionary idea. There must be a strange, invisible force, what we now call dark energy, pushing the universe apart faster and faster. Unlike dark matter, which gathers in clumps, forming galaxies, clusters, and the great cosmic web, dark energy does not clump at all. Instead, it is smoothly and evenly spread out through the entire universe. Whether you look deep inside a dense galaxy cluster or far out into the emptiest void, you'll find that the amount of dark energy is roughly the same. It fills space like an invisible mist, always there, always exerting its gentle push. This push acts like a kind of anti-gravity. It doesn't pull things together, it pushes them apart. And as the universe expands and becomes more spread out, the influence of dark energy becomes stronger compared to gravity, which gets weaker over larger distances. That means the more time passes, the more powerful dark energy becomes in shaping the future of the cosmos. This has a huge impact on how the large-scale structure of the universe changes, especially in the cosmic voids. In crowded places like galaxy clusters and the long filaments of galaxies, gravity is very strong. The pull from all that mass can resist dark energy's push. These dense regions stay together and even grow by pulling in more matter, with galaxies merging and interacting. Here, dark energy's effects are still present, but they are overpowered by gravity. But in voids, the story is completely different. Voids are enormous regions of space with very little matter, both ordinary matter like stars and gas, and dark matter. Because there is so little material, the gravitational pull in voids is extremely weak. And where gravity is weak, dark energy takes over. It's like trying to stretch a rubber sheet. The spots with knots or weights resist the stretch, but the empty spots stretch easily. Voids, being empty parts of the universe, are the places where dark energy can work most effectively. In fact, voids are expanding even faster than the rest of the universe. While the universe as a whole is growing larger with time, the voids are growing even more quickly. They are becoming bigger, emptier, and darker as dark energy pushes the remaining bits of matter farther apart. This makes voids some of the best natural laboratories for studying dark energy, because the usual interference from gravity is much weaker there. Astronomers can learn a lot about dark energy by observing voids very carefully, measuring how fast they are expanding, how their shapes evolve over time, and how the few lonely galaxies inside them behave. If dark energy is truly constant and unchanging, as suggested by Albert Einstein's idea of the cosmological constant, then voids should expand in a smooth, predictable way. But if dark energy varies over time or across space, then the patterns of void expansion might be very different. So by watching voids and studying their growth, scientists can test important ideas about what dark energy really is and how it might shape the ultimate fate of the universe. One of the best-known voids, the Bootes void, is especially important. It is one of the largest voids ever discovered and has been studied in great detail. Because it is so vast and so empty, it offers a rare and powerful opportunity to see dark energy at work, pushing, stretching, and reshaping the cosmos in silence. As time marches on, a strange and powerful force known as dark energy continues to shape the fate of the universe. This mysterious energy, which pushes space itself apart, is causing the expansion of the universe to speed up more and more as the ages pass. And this acceleration isn't just a small detail. It has enormous consequences for the future of everything we see in the cosmos, including the great empty regions known as cosmic voids. In the far future, as dark energy keeps dominating over gravity, the expansion of the universe will become so rapid that galaxies not tied together by gravity, like those in separate galaxy clusters, will begin to drift apart faster than ever before. They will move away from each other at such great speeds that eventually they will cross a point of no return, a limit beyond which their light can no longer reach us. Bit by bit, they will disappear from view, slipping beyond what we call the observable horizon. It will be as if they are vanishing into the darkness. Right now, galaxies are woven together in a vast and beautiful structure called the cosmic web, a gigantic network made up of long, thread-like filaments of galaxies and clusters. But as the universe stretches and stretches, these cosmic threads will become thinner and more fragile. Over time, the bonds between clusters will weaken, and then they will snap all together. The great web will unravel. The voids, those enormous, already mostly empty regions, will become even more desolate. Over the course of billions and eventually trillions of years, space will grow so wide and so empty that each galaxy, or small group of galaxies still bound together by gravity, will become like a lonely island floating in a dark, silent sea. They will no longer be able to see or communicate with any others, because the light from those distant galaxies will be stretched so much by the expanding space that it will become completely invisible. Its wavelength pulled so far it can no longer be detected. In that distant age, galaxies will age and fade, stars will die, and all around them, the voids will grow even larger and quieter. These vast dark regions will stand as the final symbol of an ever-accelerating universe. Giant oceans of emptiness, where only cold, stretched-out space remains, separating the last flickering lights of dying galaxies that may never know they were once part of a grand cosmic web. Trying to measure something as enormous and empty as the Bootes void might sound like trying to weigh a shadow or catch the wind in your hands. It's not at all like measuring a table with a ruler or calculating the size of a planet with satellites. The Bootes void is a colossal hole in the universe, a region so vast and so empty that it's defined not by what is there, but by what's missing, a large number of galaxies. So, how do astronomers, those tireless explorers of the cosmos, measure something that is mostly made of nothing? The answer lies in clever thinking, incredibly powerful telescopes, and a deep understanding of how light travels through space. It's like solving a mystery by gathering tiny clues scattered across the vast darkness. Scientists don't look directly at the void itself. They collect data from the few lonely galaxies hiding inside it, or from the galaxies surrounding its immense edges. Step by step, they piece together a map of this cosmic emptiness, using faint rays of ancient light that have taken millions, even billions, of years to reach us. This entire effort is a shining example of human curiosity and ingenuity, how science can paint a picture of the grand universe even with only the faintest whispers of light. The most important technique for measuring and mapping such cosmic gaps, like the Boote's void, is something called a galaxy redshift survey. Think of it like this. Imagine you're standing in a thick, foggy forest. You can't see the whole forest, only the trees. To truly understand the shape of the forest, you need to figure out where each tree is, not just side to side, but also how far away each one is from you. That way you can build a full three-dimensional image. In astronomy, galaxies are like those trees. We can see where they are in the sky, like dots on a flat map. But to understand the real shape of the universe, we need to know how far away each galaxy is. Only then can we build a three-dimensional map, one that shows not just galaxies, but also the enormous empty spaces between them. This mapping process starts with very powerful telescopes. These aren't just giant versions of the telescopes you might use in your backyard. They are highly advanced tools built to collect the faintest glimmers of light coming from galaxies unimaginably far away. Some of the biggest and best ground-based telescopes are found in places with clear and dark skies like the dry deserts of Chile, home to the European Southern Observatory's Very Large Telescope, or VLT, or atop the tall mountains of Hawaii, where the Keck Observatory stands. These telescopes have mirrors that are many meters wide, designed to soak in as much light as possible during long observing sessions. But that's not all. Space telescopes like the famous Hubble Space Telescope and the more recent and powerful James Webb Space Telescope also play a vital role. Floating high above Earth's atmosphere, these space telescopes are free from the blurring effects of air and weather. They act like giant cosmic buckets, scooping up ancient light that has travelled across the universe for hundreds of millions or even billions of years. Once a telescope captures the light from a distant galaxy, that light is passed through a special tool called a spectrograph. A spectrograph is like a very advanced prism. It splits the light into its different colours, much like how sunlight becomes a rainbow after shining through raindrops. But instead of just creating a pretty arc of colours, the spectrograph reveals a detailed barcode-like pattern, a spectrum full of dark and bright lines. These lines are extremely important. They are the unique fingerprints of the elements that exist in the galaxy. Every element in the universe, like hydrogen, helium, or oxygen, leaves a distinct mark on light. For example, hydrogen, which is the most common element in space, always shows up with the same exact pattern. When astronomers look at the spectrum of a faraway galaxy, they search for these familiar fingerprints. Now comes the crucial part. If a galaxy were not moving relative to us, the lines would appear exactly where we expect them to be. But the universe is expanding. This means nearly all distant galaxies are moving away from us. When a light source moves away, the light waves stretch out, just like the sound of a train whistle drops in pitch as it speeds away. As light waves stretch, their colour shifts toward the red end of the spectrum. This stretching of light is known as redshift. The more the light is stretched, the more redshifted it becomes, and the faster the galaxy is moving away. Astronomers can measure exactly how much the lines in the spectrum have shifted, and from that, they can calculate the galaxy's speed and distance. Thanks to the work of astronomer Edwin Hubble, we know that the farther away a galaxy is, the faster it appears to be moving away. This rule is known as Hubble's law, and it gives us a cosmic measuring stick. In other words, redshift tells us how far away a galaxy really is. By measuring the redshift of thousands, even millions of galaxies, astronomers can build a huge three-dimensional map of the universe. This map shows where galaxies are thickly clustered together in long filaments, where they form massive superclusters, and most importantly where they are not, those vast and eerie empty regions like the Boote's void. To figure out the size and shape of Boote's void, astronomers must gather an immense amount of information, especially something called redshift data, from not just thousands, but often millions of galaxies spread across huge sections of the sky. But this is no quick task. It takes years of hard, patient work and the efforts of many scientists. Giant sky surveys, such as the Sloan Digital Sky Survey, often called SDSS, and the 2-degree field galaxy redshift survey, known as 2DFGRS, were designed for this exact purpose. These are massive scientific projects that involve dedicated teams of researchers working over long periods of time, sometimes decades. They scan large parts of the night sky methodically, collecting light from hundreds or even thousands of galaxies at once. They do this using special instruments that break down the light from each galaxy into its component colours. This is called taking a spectrum. From the spectrum of a galaxy, scientists can figure out 2 very important things. First, they find out exactly where the galaxy is in the sky, its 2-dimensional location. Second, they measure how much the galaxy's light has been stretched, or redshifted, as the universe expands. This redshift tells us how far away the galaxy is. When you combine the position and the redshift of millions of galaxies, you get something incredible, a 3-dimensional map of the universe. On this map, each galaxy becomes a tiny glowing dot, and when you look at all those dots together, a grand structure starts to emerge. You see long, thread-like strands of galaxies, called filaments, spanning across space. At the points where several filaments intersect, you find dense clumps of galaxies called clusters. But most fascinating of all are the vast gaping regions where galaxies are missing. These are the voids, and among them, the Bootes void stands out as one of the largest and emptiest ever found. But finding a void like the Bootes void is not as simple as spotting a black hole or a planet. There is no solid edge or clear line that marks where it begins or ends. Instead, astronomers rely on sophisticated computer programs and mathematical methods to detect these strange regions. They look for places in their galaxy maps where the number of galaxies suddenly drops far below what is expected. It's not just about spotting a gap, it's about measuring just how empty that gap really is. To imagine this, think of plotting every galaxy as a small dot on a computer screen. In most parts of the universe, the screen would be filled with dots, some packed tightly together, others more spread out. But in a cosmic void, you would see huge blank spaces with very few or no dots at all. The Bootes void shows up on these maps as one of the most dramatic examples of emptiness, a vast cosmic bubble where galaxies are incredibly scarce. Scientists can even calculate just how empty it is by comparing its galaxy density to the average density of the universe. This measurement is called the density contrast, and in the case of the Bootes void, this contrast is extremely high. That means it is not just a little empty, it is one of the most underpopulated regions ever discovered in space. To better understand the size and shape of such voids, astronomers use a clever technique called percolation analysis. This method is a bit like watching how water flows through a sponge. Just as water finds its way through all the tiny holes and tunnels in the sponge, this analysis helps scientists see how large empty spaces in the universe are connected. The boundaries of these voids are not sharp. They don't have walls. Instead, the emptiness gradually fades into the surrounding filaments and galaxy clusters. So, the Bootes void is not a perfect sphere. It is more like a huge bubble, shaped by the gravity of the dense cosmic structures around it. It is as if matter has been pulled away from this central region and clumped together to form the walls of the cosmic web. One of the most fascinating challenges in studying the Bootes void is looking at the rare galaxies that actually live inside it. These are sometimes called lonely galaxies, because they exist in isolation, far from the crowded, bustling neighbourhoods where most galaxies live. Their existence proves something important. The Bootes void is not completely empty, it is just incredibly sparse. But these lonely galaxies are very hard to observe. They're extremely far away and often very faint, since they are not forming stars as actively as galaxies in denser regions. To study them, astronomers need to use powerful telescopes and observe for long periods of time to collect enough light. When they measure the redshift of these galaxies, they can confirm that the galaxies truly lie within the Bootes void and are not just lying in front of or behind it by chance. And by studying their shapes, the rate at which they form stars, and the amount of gas they contain, scientists can learn how galaxies behave in these peaceful, gravitationally quiet environments. These isolated galaxies are like natural experiments, They help us understand what happens when a galaxy grows up all alone, untouched by the gravitational battles that happen in crowded cosmic neighborhoods. Looking ahead, the future of void studies is very exciting. New technologies are being developed that will allow astronomers to map the universe even more clearly. Upcoming galaxy surveys will be able to see fainter and more distant galaxies than ever before. They will cover much wider parts of the sky and detect millions of galaxies, helping us refine our three-dimensional maps of the cosmos. Some of these new instruments can observe light not just in the visible spectrum but also in the infrared. This is important because infrared light can pass through cosmic dust, revealing galaxies that were previously hidden. These tools may even uncover more lonely galaxies hiding inside the Boots void. In addition, advanced computer programs and artificial intelligence are being created to sort through the enormous mountains of data these surveys will produce. These tools will help scientists quickly find and study the complex patterns in the universe, including voids and filaments. Even the faint whispers of the cosmic microwave background, the ancient light left over from the Big Bang, can help tell us more about voids. As this light travels across the universe, it passes through different cosmic landscapes. When it moves through a huge void like Bootes, its path is slightly altered, creating a tiny cold spot in the cosmic background. This faint effect is known as the integrated Sachs-Wolf effect. Though incredibly subtle and difficult to detect, these cold spots can give scientists yet another clue about the presence of large voids, confirming their influence on the universe's structure. So, measuring the Bootes void is not as simple as pointing a telescope and taking a picture. It is more like solving a vast cosmic puzzle. Astronomers must gather the faintest light from millions of galaxies, carefully measure how far away they are, and then use powerful mathematics and computer models to see the universe's grand design. The result is a beautiful, sponge-like structure filled with threads of galaxies, glowing clusters, and enormous mysterious holes like the Bootes void. Imagine you're standing beside a railway track on a quiet day. In the distance, you hear the sound of a train horn. As the train rushes toward you, the horn seems to get higher and sharper in pitch. But as soon as the train speeds past you and moves away, that same horn suddenly sounds lower and deeper. This shift in the sound's pitch isn't just your imagination. It's a real physical effect called the Doppler effect. It happens because the movement of the train changes the way the sound waves reach your ears. When the train comes closer, the sound waves get squeezed together, like ripples in a pond when something fast moves across it. The waves arrive more frequently, with shorter distances between them. This is called a shorter wavelength, and we hear a higher pitch. When the train moves away, the waves are stretched out, creating longer wavelengths, and we hear a lower pitch. This everyday experience with sound is just a small glimpse of something much bigger and more powerful happening in the universe. A similar effect applies not just to sound, but also to light, and this version plays a major role in how astronomers explore the vast reaches of space. Instead of hearing the change, scientists see the change in light. This version of the Doppler effect is known as Redshift, and it is one of the most important tools astronomers use to figure out how far away galaxies are and how fast the universe is expanding. It even helps us study huge empty regions in space, like the enormous Bootes void. To really understand redshift, let's first think about light itself. Light travels in waves, similar to how ripples spread out in water. Each wave has a wavelength, which is the distance between the peaks of two waves. The color of light depends on this wavelength. For example, red light has longer wavelengths, while blue light has shorter ones. The full range of wavelengths, from extremely long ones like radio waves to extremely short ones like gamma rays, is called the electromagnetic spectrum. Our eyes can only see a small slice of this spectrum. This visible slice contains all the colors of the rainbow, from red, with the longest visible wavelengths, to violet with the shortest. But most light in the universe is invisible to us, and astronomers need special instruments to detect it. Now, imagine applying the Doppler effect to light waves instead of sound. When a light-emitting object, like a star or a galaxy, is moving away from us, the light it sends out gets stretched during its journey. The longer these waves become, the more they shift toward the red end of the visible spectrum. This is what we call redshift. On the other hand, if something is moving toward us, its light waves get compressed, the wavelengths become shorter, and the light shifts toward the blue end of the spectrum. That's called blue shift. In most cases, especially when we're looking at very distant galaxies, we see redshift, because almost all of them are moving away from us. This isn't just because the galaxies themselves are speeding through space. In fact, something even more fascinating is happening. Space itself is expanding. Think of this using a balloon. Imagine drawing tiny dots all over a deflated balloon. As you blow it up, the surface stretches and all the dots move farther apart from each other. But notice, they're not sliding across the surface. They're staying where they are, and it's the balloon's surface that's doing the stretching. This is similar to what's happening in the universe. Galaxies aren't really flying away like rockets. Instead, the fabric of space between them is growing larger. As this space stretches, the light travelling through it also gets stretched, just like the balloon's surface. This stretching of light due to the expansion of the universe is called cosmological redshift, and it's what we mostly observe when looking at galaxies that are billions of light years away. The more distant the galaxy, the longer its light has been travelling and the more space has stretched in that time. That means we see a greater redshift the farther away something is. This idea is directly tied to the universe's steady growth since the Big Bang, which happened around 13.8 billion years ago. But how do astronomers measure this redshift? They use a device called a spectrograph, which is connected to a telescope. When the telescope captures light from a distant galaxy, the spectrograph breaks that light into its separate colours, creating a spectrum much like a rainbow. Within this spectrum, astronomers search for specific spectral lines, special patterns that act like barcodes for different chemical elements. Take hydrogen, for example. It is the most common element in the universe, and it produces a very specific pattern of lines when it emits or absorbs light. Scientists already know exactly what this hydrogen barcode looks like from experiments here on Earth. Now, when they observe the same pattern in a distant galaxy, those spectral lines will appear shifted toward the red part of the spectrum if the galaxy is moving away. It's like hearing a familiar song being played, but every note is slightly lower. The pattern is still there, but it's been moved, and the amount by which these lines have shifted gives astronomers a number they call the redshift parameter, written as the letter Z. The larger the Z value, the more the light is stretched, and that tells us the galaxy is moving away faster and is farther away in the cosmos. Some galaxies show redshifts so large that their light has been travelling for over 10 billion years before reaching Earth. That means we're not just seeing them far away, we're seeing them as they were billions of years ago, providing a time-travelling glimpse into the early universe. In the late 1920s, an American astronomer named Edwin Hubble made a discovery that forever changed how we understand the universe. By carefully studying the light from distant galaxies, Hubble noticed something astonishing. Almost every galaxy beyond our local group was moving away from us. And even more surprising, the farther away a galaxy was, the faster it seemed to be speeding off into the distance. This incredible observation became known as Hubble's law. It revealed a simple but powerful truth. A galaxy's speed of recession, how quickly it moves away from us, is directly linked to how far away it is. In other words, if one galaxy is twice as far away as another, it will also be moving away twice as fast, and its light will be stretched out, or redshifted, twice as much. This idea was revolutionary. Before Hubble's discovery, measuring how far away a galaxy was felt like trying to measure the ocean with a teacup. Slow, uncertain, and nearly impossible at great distances. But now, thanks to redshift, astronomers had a reliable cosmic ruler. They could look at the light from a galaxy, measure how much it was redshifted, and figure out how far away it was. No tape measure needed. Redshift had become the most powerful tool for measuring distances in the vast universe beyond our nearby galactic neighbours. But redshift doesn't just help us figure out distance, it also acts like a time machine. That's because light, even though it moves extremely fast, about 300,000 kilometers per second, still takes time to travel. So when we look at a faraway galaxy, we're not seeing it as it is right now. We're seeing it as it was when the light first left it, millions or even billions of years ago. For example, if a galaxy has a redshift of 1, that means its light has been travelling for around 7 to 8 billion years before reaching our telescopes. That shows us the galaxy as it looked when the universe was only about half as old as it is today. Now imagine galaxies with even higher redshifts, say 8 or 10. These are some of the most distant galaxies ever seen, and their light has been travelling across space for more than 13 billion years. We see them not as mature, majestic galaxies, but as tiny glowing seeds of what would eventually become the galaxies of today. These high redshift galaxies give us a direct window into the early universe, only a few 100 million years after the Big Bang, when the first stars and galaxies were just beginning to form. So redshift is not just a ruler, it's also a record of time, allowing astronomers to look back into the past, to witness the birth and evolution of galaxies over billions of years. But there's even more. Redshift is absolutely essential for mapping out the true shape and structure of the universe. Without it, our maps of space would be like looking at a world map with all the buildings squashed into a single flat picture. No way to tell which are near, which are far, or where the empty spaces are. You might know a building exists, but not whether it's a towering skyscraper or a tiny shed hiding behind it. Redshift adds that missing third dimension, depth. With it, astronomers can take a flat image of the sky and turn it into a three-dimensional model of the cosmic web, a vast network of filaments, clusters, and giant empty areas known as cosmic voids. On these 3D redshift maps, the universe reveals its structure. Filaments look like long, glowing strings of galaxies stretched out across space. At the intersections of these strings are galaxy clusters, bright, crowded knots of stars and galaxies, and in between them lie the great empty spaces, the cosmic voids. One of the most famous of these is the Bootes void. It was discovered when astronomers noticed something odd, a big blank area in their redshift data. They were scanning a region of the sky in the direction of the constellation Bootes when they found that, over a certain range of redshifts and therefore distances, there were far fewer galaxies than expected. It was as if someone had carved a giant invisible hole into the universe. This eerie absence turned out to be the Bootes void, a colossal cosmic cavern, so large and empty it still amazes scientists to this day. Thanks to redshift, astronomers could pinpoint the edges of this void, trace its shape, and measure its size, helping us better understand how galaxies and empty spaces are arranged across the universe. Now, redshift is incredibly useful, but it's not completely straightforward. Galaxies don't just drift along quietly with the expansion of the universe. Sometimes they have their own quirky motions, known as peculiar velocities. These are extra movements caused by nearby gravitational pulls, especially in crowded places like galaxy clusters. Because of this, a nearby galaxy might appear a little more redshifted, or even blue-shifted, moving toward us, depending on how it's moving locally. But for galaxies that are very far away, these small individual motions hardly matter. In those distant realms, the expansion of the universe itself is the overwhelming factor that stretches the light, and redshift becomes a clean, reliable measure of how far away something is. That's why astronomers use it with great confidence to map the structure of the cosmos. Our journey to understand the universe begins right where we are, on the planet we call Earth. Earth is not floating alone in space. It travels in a steady orbit around a glowing ball of fire we know as the Sun. But even the Sun is not unique. It is just one among hundreds of billions of stars that live within a much larger community, a grand spiral-shaped galaxy called the Milky Way. The Milky Way is like a cosmic city made of stars, swirling clouds of gas and fine dust, all arranged in a magnificent spiral pattern. From one end of this galaxy to the other, it stretches across a distance of about 100,000 light-years. That means if a beam of light were to travel from one edge of the Milky Way to the opposite side, it would take 100,000 years to make the journey. That is how incredibly huge our galaxy is. For many centuries, people believed the Milky Way was the whole universe. It was all we could see in the night sky, a glowing band stretching from horizon to horizon. Our tools were limited, and our ideas about space were still young. But as our telescopes improved and our understanding of the heavens deepened, a great realization dawned. The Milky Way is not the entire universe. It is just one galaxy among many, countless others scattered across the cosmos in all directions. To fully understand something as mysterious and enormous as the Bootes void, a vast, nearly empty region of space, we must take several giant steps away from our galaxy and explore the larger and larger structures that make up the universe. The Bootes void is not just a blank patch in space. It plays an important role in shaping the universe's large-scale architecture. It marks the emptier regions that lie between cosmic structures and reminds us that the universe is not smooth and even, but wildly uneven, filled with clumps of galaxies and vast gaps of almost nothing at all. The first step beyond the Milky Way takes us into our galactic neighbourhood, which scientists call the local group. This group is like a small family of galaxies bound together by gravity. It includes our Milky Way, the Andromeda Galaxy, which is even bigger than our own, and the Triangulum Galaxy, along with around 50 smaller dwarf galaxies. Altogether, the local group stretches across a region roughly 10 million light-years wide. You can think of it like a small town in the universe. The Milky Way and Andromeda are the big cities, while the dwarf galaxies are the quiet little villages. These galaxies sometimes interact with each other, and in the distant future, billions of years from now, Andromeda and the Milky Way are expected to collide and merge into one giant galaxy. But even the local group is just a small part of something much larger. When we look farther out, we find massive gatherings of galaxies called galaxy clusters. These are the true giants among cosmic structures, collections of hundreds or even thousands of galaxies, all held together by their combined gravitational pull. These galaxy clusters are like bustling cities in space, each one teeming with galactic inhabitants. Galaxy clusters can be enormous, stretching across distances from several million to tens of millions of light-years. A nearby example is the Virgo cluster, which is slowly pulling our local group toward it. The Virgo cluster contains over 1,000 galaxies and spans roughly 10 million light-years. Then there's the Coma cluster, which is even larger and more crowded, containing thousands of galaxies packed close together. But it's not just galaxies that make up these clusters. Between the galaxies lies a vast ocean of hot gas, so heated that it shines in powerful X-rays. Even more mysteriously, most of a cluster's mass is not made of stars or gas. It is made of dark matter, a strange and invisible substance that cannot be seen but exerts a strong gravitational pull. Without dark matter, the gravity of the galaxies alone would not be strong enough to hold these massive clusters together. Galaxy clusters form in the densest parts of the young universe. Gravity pulled matter together, forming these dense knots that attracted more and more galaxies over billions of years. Even now, galaxy clusters continue to grow as more galaxies fall into them, along thin, thread-like streams of matter called filaments. Beyond galaxy clusters lies an even more impressive layer of structure, the superclusters. These are not simple collections of galaxies or clusters. They are enormous networks of many galaxy groups, clusters, and individual galaxies stretched out like tangled threads across hundreds of millions of light-years. Our own local group, the Virgo cluster, and many other nearby clusters are all part of a gigantic supercluster known as Laniakea, a Hawaiian word meaning immense heaven. The Laniakea supercluster stretches across about 500 million light-years and contains the mass of more than 100,000 galaxies the size of the Milky Way. All of the galaxies inside Laniakea are slowly drifting inward, pulled by the gravity of a mysterious region known as the Great Attractor, an invisible force tugging on everything within the supercluster. But Laniakea is not the only supercluster in the universe. Others, such as the Perseus-Pisces supercluster, the Coma supercluster, and the Hercules supercluster, also span vast distances. These superclusters are like the glowing continents of the universe, where matter has gathered into the brightest and densest parts of the cosmic landscape. They are not tightly bound like clusters are, but they do share a common flow, a gentle, gravitational pull that connects their many parts. All these structures, galaxies, clusters, and superclusters, are part of something even bigger and more breathtaking, the cosmic web. This is the grand architecture of the universe, the ultimate map of matter on the largest scale we can observe. The cosmic web stretches across the entire observable universe, forming an intricate network that resembles a vast three-dimensional spiderweb or a sponge with endless tunnels and threads. The cosmic web is made up of three main parts. First, there are the filaments, long thread-like chains of galaxies that can stretch for hundreds of millions of light-years. Next are the nodes, or clusters, which sit at the intersections of these filaments, where matter is densest and galaxies gather in great numbers. And finally, there are the voids, enormous regions of space with very few galaxies, like great cosmic deserts lying between the bustling galactic highways. Superclusters like Laniakea, make up the brightest and most massive parts of the filaments and nodes. These are the spots where gravity has pulled matter together most strongly. And in between these glowing strands lie the voids, such as the Bootes void, which help define the shape and structure of the universe by showing us where matter is absent. So, where exactly does the Bootes void belong in the grand structure of the universe? To understand this, we need to zoom out, far beyond planets, stars, galaxies, and even clusters of galaxies. The Bootes void is not a galaxy. It is not part of a small group of galaxies, nor is it a massive galaxy cluster, or even one of the giant superclusters that hold many clusters together. In fact, it is the complete opposite of all those things. The Bootes void is one of the largest and most dramatic examples of what scientists call a cosmic void. Cosmic voids are vast, empty regions in the universe, regions where there is very little matter, very few galaxies, and almost no activity. These voids make up one of the three main building blocks of the cosmic web, which is the huge interconnected structure that forms the universe on the largest scales. While galaxies, clusters, and superclusters form the threads and knots of this web, voids are the enormous empty spaces in between. The Bootes void is like a gigantic bubble of nothingness. It stretches across a staggering distance, roughly 250 million light-years from one side to the other. That's larger than many entire superclusters, although a few of the very biggest superclusters can still be bigger. Still, the sheer scale of the Bootes void highlights just how empty and vast it truly is. While a supercluster is a massive pile-up of matter, the Bootes void is a massive absence of matter. If the universe were a map of continents and oceans, the continents would be the dense filaments and superclusters, while the Bootes void would be one of the most enormous oceans of emptiness in between. It acts like a huge buffer zone, sitting quietly between the bustling continents of galaxies. It is not just an empty space chosen at random, it is an emptiness carved out by gravity itself. Over billions of years, the gravity of the surrounding structures slowly pulled matter away from the center of the void, making it even emptier than it once was. Because of this, the Bootes void plays an important role in shaping the cosmic web. It helps define the edges of the largest structures in the universe. Its position is not just a curiosity. It's a clue to how the entire universe is arranged. The void reminds us that the universe is not filled evenly with matter. Instead, matter is gathered in thick clumps, and between those clumps lie vast, silent gaps like the Bootes void. Understanding where the Bootes void fits in this cosmic puzzle helps us better understand the universe itself, from our tiny planet to the farthest reaches of space. It teaches us about how galaxies form, how gravity works over vast distances, and how the universe grows and changes over time. The very pattern of the universe, this grand web of filaments, clusters, and voids, was shaped by two powerful forces: gravity, which pulls matter together, and the expansion of space, which pushes everything apart. The Bootes void, because of its enormous size and incredible emptiness, gives astronomers a special place to study these forces in action. Since it has so little matter, the effects of gravity are weak there, which means it's a great place to observe the mysterious force known as dark energy, the force that is making the universe expand faster and faster. By studying places like the Bootes void, far beyond our galaxy, and even beyond the largest galaxy clusters, we begin to see the universe not just as a place full of stars and galaxies, but also as a place of vast, quiet, breathtaking emptiness. This emptiness is not meaningless. It is part of the design, helping shape the universe just as much as the matter does. And in this beautiful, delicate balance between fullness and emptiness, we find a deeper, more awe-inspiring understanding of the cosmos. The universe is not packed solid with galaxies, clusters, and superclusters. Mixed in with those are vast stretches of almost nothing. These regions are known as cosmic voids, huge areas of space where there are very few galaxies and very little ordinary matter. Though we often focus on the bright parts of the universe, the galaxies, the stars, and the glowing clouds of gas, the empty parts are just as important. They are key pieces of the puzzle that make up the cosmic web, the universe's enormous sponge-like structure. While the Bootes void stands out because of how gigantic it is and how early it was discovered, it is not alone. Many other voids exist across the universe. Each one of these empty places helps scientists understand how the universe is put together and how it has changed over time. By studying other voids, researchers can see that the Bootes void is part of a larger pattern, not a strange exception. These studies reveal the hidden forces that shape the universe and explain how such gigantic empty spaces could come to exist in the first place. Cosmic voids share some common traits. First and foremost, they are places where there are far fewer galaxies and much less matter than in the average parts of the universe. They are not completely empty. Some particles and a few galaxies are still inside them, but their overall content is extremely thin. In fact, the amount of regular matter inside a typical void might be only 1/10, or even less, of what you'd find elsewhere in the universe. Voids can be tens of millions to hundreds of millions of light years across. Some are so large that they form bubble-like holes in the cosmic web. Though mostly free of stars and gas, voids still contain dark matter, although in small amounts. More importantly, they are filled with dark energy, a mysterious force that pushes the universe apart. Dark energy is spread out evenly across space, and inside voids, where gravity is weak, its effect becomes more noticeable. As a result, voids slowly grow larger over time, as dark energy pushes matter farther away from the center. Even inside these giant quiet regions, a few lonely galaxies can still be found. These isolated galaxies live far from their neighbors and often evolve differently than those in crowded clusters. Because they are not shaped by frequent interactions or mergers, they can offer unique clues about galaxy evolution. Although voids have some things in common, they are not all the same. They vary widely in shape, size, and structure. Some, like the Bootes void, are gigantic. The Bootes void is about 250 million light-years wide, making it one of the biggest voids ever found. Others are smaller, perhaps only 50 or 100 million light-years across. The size of a void often depends on its surroundings. Larger voids are usually found between bigger superclusters of galaxies. Their shapes are rarely neat or spherical. Instead, they tend to be stretched out, lumpy, or twisted, shaped over billions of years by the way gravity has pulled matter away from their centers. Some voids are fairly isolated, while others connect with neighboring voids to form huge empty regions, almost like tunnels or caves in the structure of the universe. These differences in size and shape tell scientists a lot about how the universe started and how gravity and dark energy have sculpted it over time. They offer valuable clues about the very early conditions of the cosmos and help refine our models of how galaxies formed and moved. One of the closest voids to Earth is called the local void. Unlike the Bootes void, which is far away, the local void lies right next to our own galactic neighborhood. It separates our local group of galaxies, which includes both the Milky Way and the Andromeda Galaxy, from other nearby galaxy clusters. This nearby void doesn't just sit quietly in space, it actually affects how our group of galaxies moves. Because it contains so little matter, the local void does not pull on us with much gravitational force. Meanwhile, denser regions like the Virgo cluster do pull on us more strongly. As a result, we are slowly moving away from the local void and toward these more crowded areas. This motion is part of what astronomers call our peculiar velocity, the way our galaxy moves through space beyond the basic expansion of the universe. The local void is not as huge as the Bootes void, but it is still very large, stretching perhaps 100 to 150 million light-years across. And because it is so close to us, it plays an important role in our understanding of how empty space affects motion in the universe. Another vast and nearly empty region is known as the northern local supervoid, also called the sculptor void. This void is much larger than the local void and is roughly spherical in shape. It measures about 300 million light-years in diameter and lies not far from our own local group. Though it has not gained as much attention as the Bootes void, it is another clear example of the universe's sponge-like layout, full of both filled and empty regions. Studying this supervoid helps astronomers better understand how voids are arranged across the cosmos and how they influence the movements of nearby galaxies. Perhaps the most fascinating and mysterious void being studied today is the Eridanus supervoid. This particular void might help explain a strange feature in the cosmic microwave background, or CMB, the ancient light left over from the Big Bang, which is spread across the entire sky. Although the CMB is mostly the same everywhere, it has small temperature differences in different areas. One region, known as the CMB cold spot, is unusually cold, colder than scientists would expect. One leading idea is that a gigantic cosmic void lies in that direction. If true, this Eridanus supervoid could be around 1 billion light-years across, possibly making it even larger than the Bootes void. The theory is that as light from the Big Bang passed through this enormous empty region, it lost a tiny bit of energy, making the cold spot appear cooler than the surrounding areas. Scientists are still studying this region carefully, using galaxy surveys and three-dimensional maps to see whether this supervoid is real and how large it actually is. If it exists, the Eridanus supervoid would be one of the largest structures ever discovered, and an incredible example of how even the emptiest places in the universe can shape what we see, all the way back to the beginning of time. All cosmic voids, whether we are talking about the local void close to our own Milky Way, the enormous Bootes void, or the mysterious and still debated Eridanus supervoid, have a lot in common. These vast, nearly empty regions of space were shaped by the same forces that built the entire universe. In the very beginning, just after the Big Bang, the universe was filled with tiny ripples. Some places were a little denser, while others were a bit emptier. The areas that started off slightly emptier didn't attract much matter. Instead, gravity pulled matter away from them and into the denser regions, which grew into galaxies, clusters, and the long filaments that form the cosmic web. As billions of years passed, the universe kept expanding, stretching everything farther apart. In the voids, where there was already very little matter, this expansion was even more dramatic. On top of that, an invisible force known as dark energy started to dominate. It acts like a kind of anti-gravity, pushing the universe to expand faster and faster, and where there's not much matter, like in voids, dark energy has the upper hand. This makes these already empty regions grow even emptier. Even so, voids are not completely deserted. Scattered within them are lonely galaxies, individual islands of stars that formed far away from the crowded cities of galaxies we see in clusters. These isolated galaxies are especially interesting to astronomers because they show how galaxies grow and change when they're left all alone, far from the influence of other galaxies. So in the big picture, all voids, big or small, are the result of the same cosmic recipe. They are part of the universe's large-scale structure, a web-like pattern where matter clumps together in some places and is nearly absent in others. Voids are not random gaps. They are physical evidence of how gravity, dark matter, and dark energy work together on the largest possible scales. But despite these similarities, not all voids are exactly the same. One of the biggest differences is simply their size. The Bootes void, for example, is absolutely gigantic. It stands out as one of the largest known voids in the entire universe. Its enormous scale shocked astronomers when it was first discovered in the year 1981. While many other voids are much smaller, the Bootes void's vastness makes it special. Another difference lies in how empty each void is. While all voids have fewer galaxies than average, some are just a bit underdense, while others, like Bootes, are almost entirely empty. This difference depends on how they formed and what the surrounding environment is like. The Bootes void is also unique because the few galaxies it does contain are extremely isolated. Perhaps the most isolated galaxies we know of. These lonely wanderers are truly cut off from the rest of the universe, floating in silence across hundreds of millions of light-years of darkness. The Bootes void also holds a special place in the history of astronomy. It was one of the first giant voids ever discovered, and gave scientists their first dramatic clue that the universe was not just filled with stars and galaxies, but also with vast spaces of almost nothing. Its discovery helped confirm the idea of the cosmic web, a huge interconnected pattern where matter forms long strands and empty bubbles. This realization marked a turning point, pushing astronomers to start mapping out the full structure of the universe and search for other voids like it. Studying multiple voids across the universe is incredibly important. By comparing them, looking at how many there are, how big they tend to be, how empty they are, and where they are located, scientists can test their theories about how the universe formed and grew. If the models we use to understand the cosmos can't explain voids properly, then those models need to be improved. Voids, especially the most extreme ones like the Bootes void, or the cold spot in the cosmic microwave background, are powerful tools for learning more about dark energy. By observing how fast these empty regions expand and how the few galaxies inside them evolve, scientists gather important clues about what dark energy is and how it works. Voids are also key to understanding how a galaxy's environment affects its life. Galaxies in crowded places like clusters interact with their neighbours all the time, through gravity, collisions and bursts of radiation. But galaxies and voids live a quiet, lonely life. Comparing the two helps us understand how galaxies grow differently, depending on where they live. And there's even more. Astronomers are now looking at how individual voids might be connected, forming enormous networks of emptiness, huge tunnels and channels of space with almost no matter at all. This shows that voids aren't just isolated pockets. They're part of an even bigger system, a complex structure of empty and filled regions that stretches across the universe like a cosmic lacework. These giant gaps aren't just nothing. They are dynamic, active regions where the effects of cosmic expansion are most visible. The Bootes void, while an extraordinary and separate entity, is just one piece of this grand puzzle. It reminds us that the universe is not just a place of stars and galaxies. It is also a place where vast emptiness plays an essential role in the design of everything. In the silent, haunting vastness of the Bootes void, we find not a void of meaning, but a profound part of the universe's story, where gravity, dark matter and dark energy shape even the quietest corners of existence. Picture a world not so different from our own. A planet filled with intelligent beings, curious, inventive, and driven by a deep desire to understand the universe around them. They build machines, ask big questions, and dream of the stars. But unlike us, these beings are not nestled inside a bustling galaxy cluster or a well-connected corner of the cosmos. Instead, their home lies in one of the loneliest places imaginable, far out in the cosmic wilderness, in a tiny, quiet galaxy adrift in the heart of the Bootes void. This enormous void is one of the largest known regions of almost empty space in the entire universe. It stretches across a mind-boggling distance, roughly 330 million light-years wide. Now imagine a small galaxy floating alone inside it, and imagine a civilization growing up there, surrounded on all sides not by the light of distant stars, but by overwhelming darkness. What would life be like for them? How would their science, their sense of purpose, and their very understanding of the cosmos be shaped by this endless silence? Let's begin with something simple, something we all share no matter where we are in the universe: the night sky. On Earth, even from cities full of bright lights, we can usually see a few stars. From darker, rural areas, we see thousands of stars, and sometimes we can even spot the faint haze of the Milky Way stretching like a glowing ribbon across the sky. If you're lucky and know where to look, you might even glimpse the Andromeda Galaxy, a hazy little smudge of light more than 2 million light-years away. But in this faraway void, the view would be drastically different. When these beings look up at the sky, they would see only their own stars, those that belong to their isolated home galaxy. The rest of the sky, a vast, pitch-black emptiness. No shimmering galaxies, no grand clusters, no hints of a universe filled with countless other worlds. Just darkness. Their own galaxy might appear beautiful, perhaps a delicate spiral or a scattered cloud of stars, but beyond it would lie a darkness so deep and so total that it might feel as though they were truly alone. For this civilization, the closest galaxy beyond their own would not be a mere few million light-years away like Andromeda is to us. Instead, the nearest cosmic neighbour might be tens of millions, or even hundreds of millions, of light-years distant. That's so far that even if light from those galaxies began travelling toward them when dinosaurs still walk the Earth, it might still not have arrived. And even when it does, it would be so faint that no eye, no matter how sharp, could ever detect it without the aid of incredibly advanced telescopes. Unlike our astronomers, who can see rich tapestries of galactic collisions and glowing webs of galaxies forming long chains and clusters, astronomers in the void would see nothing. Their home galaxy would look like a lone island floating in a black, starless ocean. Early scientists on their planet might even believe that their galaxy is the entire universe. After all, if you see nothing beyond your own starry shores, wouldn't you assume you're alone? For Earth scientists, the journey to understanding the universe was long, but the clues were all around us, nearby galaxies, clusters of galaxies, and eventually the vast structures of the cosmic web. But for a civilization in the Buddha's void, every discovery beyond their galaxy would be like trying to hear a whisper across a hurricane. Even detecting another galaxy would be a groundbreaking moment, requiring enormous telescopes with light-gathering power far beyond what early human astronomers had. And once those faint galaxies were found, figuring out how far away they are would be incredibly difficult. The light would be too weak to study easily, and gathering enough of it to measure redshift, a key tool for calculating cosmic distances, would take patience, power, and persistence. Their version of Edwin Hubble, the astronomer who first showed that the universe is expanding in the year 1929, would have an even steeper hill to climb. The expansion of the universe would still be happening, but in such a calm, empty area, it would be harder to measure with precision. Because they would have no evidence of galactic filaments or galaxy clusters for a very long time, their early theories about the universe might be very different from ours. They might imagine that the universe is made up of just a few scattered galaxies, far apart and unconnected, rather than woven into a grand web. Still, by carefully studying the movement of stars in their own galaxy, they might uncover signs of dark matter, just as we did. But when it comes to dark energy, the force believed to be pushing the universe to expand faster and faster, they might actually detect it sooner than we did. Because their galaxy is so alone, there would be very little gravity from nearby galaxies to interfere with the effects of dark energy. In this quiet, clean environment, the accelerated expansion of the universe might stand out more clearly, like watching a balloon inflate in a still room, instead of in the middle of a windstorm. This might lead them to a much earlier understanding of the universe's lonely future, and perhaps to a much deeper sense of cosmic isolation. Their science and technology would also take a different path. On Earth, we dream of visiting other galaxies or sending probes to explore the vastness of space. Andromeda, though far, is still visible, and one day it will collide with our Milky Way. These possibilities fuel our curiosity. But in the Buddha's void, there would be no visible target, no nearby galaxies to aim for. The next closest destination might be so far away that it would take millions or even billions of years to reach, even at speeds close to that of light. Would that stop them from trying? Maybe, but maybe not. The loneliness of their galaxy might inspire them to dream even bigger, to build faster, more daring spacecraft, to look deeper and ask, are we truly alone? The longing to find another civilization might become a central part of their culture, an obsession that fuels generation after generation of scientists, engineers, and explorers. From a societal and philosophical point of view, life in such a lonely place would feel very different from life in our busy corner of the cosmos. The question, are we alone, would carry much more weight. For us, this is a question of curiosity. We know that our galaxy alone holds hundreds of billions of stars, and our telescopes show us that the universe contains many millions of other galaxies, so we tend to believe that if life exists elsewhere, it's only a matter of time before we find it. But for a civilization trapped in the stillness of a cosmic void, things would not feel so hopeful. The silence surrounding them would seem endless. They might truly believe that they are the only intelligent beings in the entire universe. This sense of isolation could shape their culture in powerful ways. They might see themselves as the only flame of consciousness in a vast ocean of darkness, a rare, perhaps even sacred spark of life. Their philosophies and religions might be built around themes like solitude, survival, and the incredible value of their own existence. Because they are so far from other galaxies, they would not face the same cosmic threats that we do. They would not need to worry about galaxies crashing into one another, or radiation from faraway exploding stars bombarding their world. Most of the dangers they would face would come only from within their own galaxy or solar system. This might make them more focused on protecting and preserving their home galaxy, rather than imagining threats or adventures beyond it. Their view of time and the universe would also be different. Eventually they might invent powerful telescopes, strong enough to catch the faint glow from the closest galaxies at the edges of the void. But by the time that light reaches them, it would be incredibly old, hundreds of millions, or even a full billion years old. What they see in the sky would not be the present universe, but the distant past. To them, the wider cosmos would always be history, never now. Real-time interaction with other civilizations, if they even exist, would be impossible. Any idea of making contact would remain forever in the realm of philosophy, not reality. This would likely lead them to care more about their own present and their local environment, rather than dreaming about the rest of the universe. They would be rooted in the here and now of their own galaxy, with the wider cosmos always looking like a beautiful, unreachable memory. When it comes to survival, they would have to rely completely on the materials and energy available in their single galaxy. There would be no way to import rare elements from other galaxies, or to escape to a new galactic home if something went wrong. Every drop of water, every ounce of metal, and every useful planet would need to be carefully managed and protected. This could inspire a powerful sense of responsibility toward the environment and a culture based on sustainability, long-term thinking, and careful planning. Their population and technology would also be limited by what their galaxy could provide. They would not think of the universe as an open field to conquer, but as a closed system to preserve. This might lead to social structures that value balance and efficiency above expansion. Their scientists and engineers might develop amazing ways to recycle, conserve, and innovate just to make life last for billions of years in their isolated galactic island. Even biological evolution might be slightly different in the void. In our part of the universe, galaxies are packed more tightly together, and cosmic rays, high-energy particles from supernovae and other violent events, are more common. But in a lonely void galaxy, the amount of these cosmic rays coming from outside the galaxy might be much lower. This could result in fewer radiation-related mutations in living creatures. Though this effect might be small, over billions of years it could gently shape life in unique ways. Still, most biological pressures would come from local events, like radiation from stars within their own galaxy, rather than from the distant cosmos. The universe is not a still, silent stage where cosmic events simply play out. It is alive in its own mysterious way, always moving, always changing. It is growing larger with time, and not just growing, but doing so faster and faster. One of the most astonishing scientific discoveries of the 20th century was this: the universe is not just expanding. The speed of that expansion is increasing. This expansion of space itself, the very fabric of the cosmos, affects everything, from single galaxies to the vast web of matter stretching across billions of light years. It plays a huge part in shaping the largest and emptiest parts of the universe, enormous cosmic voids like the breathtaking Booty's void. While gravity works like a cosmic glue, pulling matter together, the expansion of space works in the opposite way, pulling everything apart. And in the most empty regions of the universe, where there is already very little matter, this push from expansion takes over completely, stretching those spaces even more and making them emptier with time. The idea that the universe is expanding was firmly proven in the late 1920s by an American astronomer named Edwin Hubble. By looking at faraway galaxies and measuring something called redshift, which is how light stretches as galaxies move away, he discovered something incredible. Nearly all galaxies outside our nearby neighbourhood are moving away from us. Even more amazing, the farther away a galaxy is, the faster it is moving. This became known as Hubble's law. But galaxies aren't flying away like pieces of an exploding bomb. Instead, it is the space between galaxies that is stretching. It's like drawing dots on a balloon. As you blow it up, the dots don't move on their own. It's the balloon that expands, and the distance between the dots increases. In the same way, galaxies aren't moving through space. Space itself is growing, and it carries the galaxies along with it. To understand how this affects the vast empty regions, the voids, it's important to see the difference between things moving through space and the expansion of space itself. On smaller scales, like inside our solar system, or even inside a group of galaxies like our local group, gravity is strong enough to keep everything tightly held together. The Earth doesn't drift away from the Sun. The Sun doesn't fly away from the centre of the Milky Way. The Milky Way and the nearby Andromeda galaxy are not being torn apart. Gravity's pull is much stronger than the slow stretch of space at these short distances. But when we look at the very large scales, beyond galaxy clusters and superclusters, gravity starts to lose its grip. It becomes too weak to hold distant galaxies together, and this is where the expansion of space really takes over. At this grand scale, the universe stretches more freely. pulling galaxies apart and changing how matter is spread out. Areas where gravity clumps things together become the glowing filaments of the cosmic web, but the places where gravity is weakest become the vast, dark cosmic voids. These voids are not just leftover spaces. The universe's expansion helps them grow. Think of a giant web made of rubber bands with tiny marbles stuck at the points where the bands meet. As you stretch the entire web, the marbles that are close together stay somewhat close because they're glued with strong gravity. But the spaces between the marbles, especially where there were already fewer marbles, stretch a lot more. That's what happens in voids. If there were already few galaxies in one spot, the expansion makes them move even farther apart, making the space even emptier. This process keeps going. As the universe gets older, voids do not stay the same. They grow, becoming larger, lonelier, and more desolate. The Bootes void, already one of the biggest and emptiest places ever found, continues to expand every moment. One of the key reasons this is happening, especially now in the current era of the universe, is something called dark energy. For a long time, gravity slowed the universe's expansion down. But in the late 1990s, astronomers observed distant exploding stars, supernovae, and found something unexpected. The expansion of the universe was not slowing down, it was speeding up. This shocking discovery led to the idea of dark energy, a mysterious force or energy that pushes space apart. It acts like a kind of anti-gravity, and it seems to be spread evenly throughout the universe. It doesn't matter whether it's inside a dense galaxy or a huge empty void, the strength of dark energy is the same everywhere. In places where there's a lot of matter, like galaxy clusters, gravity is still strong and can mostly cancel out the push of dark energy. But in the lonely, underfilled voids, gravity is very weak. Here, the power of dark energy becomes the main force. There isn't enough matter to slow it down. So the voids are not just drifting apart gently, they are being pushed apart, and this push is speeding up. They're growing faster than they would under gravity alone. Voids are the perfect place to see what dark energy is doing, because there's not much else around to hide its effects. That's why huge voids like the Bootes void are so valuable for science. By watching how they change over time, how fast they grow, and how the few galaxies inside them move, astronomers can learn more about what dark energy is and how it works. If dark energy stays the same over time, voids should grow in a predictable way. But if it changes or behaves differently in different places, voids will tell us. These empty cosmic landscapes allow scientists to study dark energy more clearly than in crowded, gravity-heavy areas of the universe. The Bootes void, being so vast and clearly defined, is one of the best places to study this deep mystery of modern physics. As the universe continues its journey of expansion powered by dark energy, we get a glimpse of what might happen in the very far future. In billions and trillions of years, the galaxies that are not held together by gravity will drift away so fast that their light will become stretched beyond detection. They will disappear from our view completely, crossing the edge of our observable universe. The glowing threads of the cosmic web will stretch and thin out. The connections between galaxy clusters will weaken and break. The voids, already huge and haunting, will swell into even greater, deeper emptiness. Any galaxy that happens to be trapped inside a void will become totally isolated, cut off from all others,